My name is Elvira de Mejia, a professor in food science and human nutrition, the director of the Division of Nutritional Sciences at the University of Illinois, and a past presidential fellow at the University of Illinois system. I'm humble and thankful to facilitate this important and urgent initiative. I thank the president of the University of Illinois, Dr. Tim Kaline, for his leadership and enthusiasm, recognizing the need and the opportunity that I-MMAS represents. Welcome to this third symposium of the I-MMAS initiative, which is the University of Illinois system, Mexican and Mexican-American Student Initiative.
Thank you, Elvira, and good morning and welcome. Bienvenidos to this I-MMAS Symposium on Energy. I'm incredibly pleased that I-MMAS, which was launched just a little over a year ago, continues to gain impressive momentum in cultivating cross-border collaboration to address critical issues for our planet. This is our third I-MMAS Symposium in that short time. My congratulations to Dr. Castaño and Chamorro and to your teams on a truly impressive achievement. One of the major goals when I-MMAS was created was to begin providing more opportunities for students to travel between our universities. On our end, we are providing life-changing educational opportunities for more Mexican students at our universities in Urbana-Champaign, Chicago, and Springfield, and I'm very excited about this. But we are also building deep connections around research and discovery, links between the brilliant minds at work in our three universities in Illinois and those at our partner university, the National Autonomous University of Mexico, UNAM. Through these developing networks, we can work together to create opportunities for the people of Mexico and the people of Illinois and solve problems that affect all of us. Leveraging the combined research power of our two universities, leading experts over the next several hours will dig deeper into issues that are fundamental to our shared future. Our goal is to help people better understand the global energy crisis, discuss issues, and explore alternative solutions that will make us less reliant on non-renewable energy sources and less vulnerable to their negative impacts on our environment and health. The adverse effects of climate change from non-renewable energy sources are familiar. They exist in the form of rising temperatures, dramatically changing weather patterns, and the destruction of vital ecosystems. Non-renewable energy sources emit air pollutants, create land and water pollution, generate waste, and negatively affect people's health. Current trends in energy use may be good news for furthering the kinds of essential research and discovery that you'll see on display here today. According to the International Energy Agency, the world's renewable energy capacity increased 45% in 2020, the largest annual rate of increase since 1999, reflecting what the IEA termed an unprecedented boom in solar and wind energy. The agency further noted that renewable power was the sole energy source for which demand increased during 2020, while consumption of all other fuels declined. And it predicted that large capacity gains in renewable energy will become the new normal in 2021 and 2022, with increases similar to 2020's record total. Still, it's understood that we must invest more and find new solutions, continuing these gains to achieve net zero goals and safeguard our planet. And that's where this group comes in. The list of topics on today's agenda demonstrates a real commitment to furthering these positive trends. The research and discoveries by our faculty and students have the potential to help meet energy demands while creating a smaller environmental footprint, alleviating health risks, and addressing growing problems like energy security. Researchers who are among the experts in their fields are part of this symposium, and will lead discussions around different ways to produce, convert, and store energy with fewer environmental and health impacts. You'll be part of conversations on enhanced geothermal systems and biofuel production from wastewater and organic wastes, on key issues and solutions in wind and hydroelectric energy, and much more. Just as important, today's symposium will offer the chance to build a platform for researchers to connect, communicate, and build teams to work together going forward. All of us must be working together to build that way forward, and solutions will come en masse. It gives me a great sense of pride that together our universities can be a force for good and drive the changes that are necessary to build a prosperous, sustainable future for Mexico, Illinois, and all of North America. So again, bienvenidos y muchas gracias. Thank you so much for being a part of this symposium and sharing your expertise, your energy, and your commitment to creating a better tomorrow. We hope this gathering offers you the opportunity to make new connections and to generate the kinds of ideas that these pressing challenges demand.
Thank you very much, President Kalin, for your leadership in I-MMAS and for your kind remarks for today's symposium. Now it's my great distinction to introduce Trustee Ricardo Estrada, member of the Board of Trustees, the governing body at the University of Illinois. Trustee Estrada's presence is very significant, not just because he was born in Mexico, but because of his leadership, eminent professional career, and support to the Latinx community. Muchas gracias, Trustee Estrada, por estar aquí con nosotros. Estamos muy orgullosos de usted por ser un distinguido miembro de la comunidad, miembro de la Junta de Gobierno de la Universidad de Illinois. Su presencia es extremadamente significativa porque usted nació en México y por su gran liderazgo, su carrera profesional y su apoyo a la comunidad latina. Thank you. Gracias.
Doctora de Mejía, muchas gracias a usted y felicidades otra vez por tomar con tanta urgencia este tema que tenemos hoy y en especial la colaboración que tenemos aquí en el sistema de la Universidad de Illinois con UNAM y con todas las universidades del hemisferio. Quería darle a todos la bienvenida hoy de parte de la Junta Directiva de la Universidad de Illinois. Como dice la doctora de Mejía, soy nacido en Guanajuato, México. Llegué aquí como migrante a los 7 años. Listen, let me give a welcome to everybody on behalf of the University of Illinois system, and especially let me thank Doctora Elvira de Mejía, also President Kalin, and the rest of the board of the University of Illinois. But a special thank you to El Rector Enrique Grau Wiechers, who greeted us very warmly at UNAM in 2016 and 2017. So thank you for this. I come to you not only as a trustee of the University of Illinois, but a member of the board of 3 important institutions here in Illinois. Commonwealth Edison, which is one of the providers that provides the biggest provider of electricity in the region. Certainly, we are using nuclear and other ways to power, but increasingly we have to care about the environment and sustainability for everybody. The University of Illinois certainly is one of the great universities in the hemisphere, and if not the world, and it has a responsibility to make certain that our research and our studies continue to push us in the direction of a better world. I'm a member of the board of METRA, which is the regional train carrier here in the Illinois Cook County system, and a member of the Navy Pier, which is the region's most important tourist attraction. I tell you all this because they're interconnected. The university providing the great research that allows us to continue to flourish, the companies that provide energy for the future, and its responsibility to be a good steward of this environment, the regional carriers that are using millions of liters of diesel that have a responsibility to this environment as well, and I look to you for solutions. And finally, for Navy Pier, it's at our lakefront, one of the greatest freshwater reserves in the world. And again, together, we all have the responsibility to care for this. Again, muchísimas gracias a todos. Voy a estar aquí en este simposio por todo el día y espero aprender muchísimo de todos y les doy otra vez la bienvenida y gracias, doctora de Mejía.
Muchas gracias, Trustee Estrada. Le agradecemos mucho que esté aquí. Thank you very much for being with us today and for your leadership also at the University of Illinois. Thank you very much. So now, Dr. Víctor Castaño, a distinguished scientist and researcher at UNAM, Mexican Academy of Engineers, is a member of the Mexican Academy of Engineers, will continue introducing the rector of UNAM.
Thank you, Professor de Mejia. Good morning and welcome to all. It is indeed my great honor and pleasure to introduce Dr. Enrique Luis Graue Bichers, Rector of the Universidad Nacional Autónoma de México, UNAM. Dr. Graue is a very distinguished ophthalmologist whose academic and professional activities have been recognized internationally. Dr. Graue is also known for his strong commitment to social and educational initiatives and for his leadership in higher education efforts in Mexico and abroad. We thank Dr. Graue for agreeing to participate in this event.
Dr. Timothy Keeling, President of the University of Illinois System. Mr. Ricardo Estrada, member of the Board of Trustees of the University of Illinois. Dr. Elvira de Mejia, University of Illinois, and professors and students of both communities, UNAM and the University of Illinois System. As President or Rector of the National Autonomous University of Mexico, it's a great pleasure to give you the warmest welcome to this first joint symposium on energy organized by our institutions. This is one step ahead to enhance collaboration, teamwork, and exchange of ideas between our communities. Last year, Dr. Keeling, President of the University, and I signed an agreement to promote cultural, scientific, and academic activities in areas of mutual interest. The symposium is going to start today as a result of the Mexican and Mexican-American Students Initiative, will we hopefully mark the beginning of many other activities that will draw important lessons for the common challenges that the world is facing today. Its aim is to promote synergies among scientists based in Mexico and Illinois, who work on energy-related research and technological development in our common fight against climate change. Thank you very much to all the people involved in the organization of this symposium. I am very grateful for this initiative and for the constant support to the Mexican-American communities within University of Illinois System. Dr. Keeling and I are convinced that working together is the best way to enhance research, education, and bilateral development. Thank you very much for your attention.
Dr. Castaño.
Thank you very much. I have been asked to speak a little about the interaction between the University of Illinois System and UNAM. Dear colleagues, authorities, students, and friends of the University of Illinois and of UNAM. The National Autonomous University of Mexico and the University of Illinois system have agreed to plan and carry on joint research projects under Clause 2.e of the Memorandum of Understanding signed by the two institutions in 2021. The two institutions have accordingly agreed to establish a joint seed research grants program starting with the academic year 2022-23. This program will fund projects in three key thematic areas: food and health, water, and energy. The overreaching goal is to contribute to solving problems related to poverty, the environment, and sustainable well-being on both Mexico and the USA. Transdisciplinary approaches will be particularly welcome in this initiative. Every year, starting 2022, both universities will have a joint open request for proposals, soliciting proposals from their faculty. Only joint proposals with at least one principal investigator from each university will be eligible to apply for funding under this program. Also, only tenure-track faculty can serve as principal investigators. All proposals will be evaluated by a joint review committee of faculty and scientists appointed by the president of the University of Illinois system and director of the National Autonomous University of Mexico or their designees. UEUC and UNAM will have equal number of members on the joint review committee. Evaluation criteria will include, of course, technical quality, the relevance of the topic, the degree of collaboration and interaction, evidence of prior collaborative work, graduate or undergraduate students' participation. I would like to take this opportunity to recognize and thank Dr. Enrique Graue and Dr. Timothy Killing for their support and encouragement to this program, which is a groundbreaking initiative that I hope will lead to other collaboration initiatives on both countries. Finally, I'm very grateful to Professor Elvira de Mejia, Professor Leonardo Chamorro, and Ms. Nancy Salinas for their great work and dedication, which made possible for all of us to enjoy this event today. To all the presenters for their valuable contributions, and to all the attendees and participants. Thank you all.
Thank you very much, Dr. Castaño. Thank you all for your kind words. The objective of this symposium is to promote strategic synergies among scientists in Mexico and Illinois on energy-related research and development. Now we're interested, if you are interested in solar, wind, marine, geothermal energy and storage, you can remain in this room. If you, on the other hand, are interested in bioenergy and infrastructure, then in few minutes, not yet, in few minutes, you will move to room 2. So let me just say that there will be a series of presentations, 10 minutes each, by outstanding scientists from Mexico and Illinois. Please write your questions in the chat, and we will make sure to request the speakers to answer your questions later if time does not allow to answer all the questions during the symposium. The symposium will be recorded, and thank you to all the speakers for the meaningful and engaging presentations. I hope this symposium will spark new collaborations, new discoveries, and then many problems will be solved. Thank you for your willingness to share your knowledge and for working together for the well-being of humankind. And there are many people, I cannot name all of them, that are responsible for the success of this symposium. So I thank especially Dr. Leonardo Chamorro and Dr. Victor Castaño for their leadership preparing this very, very interesting and useful symposium. So now I'll turn it to Dr. Chamorro, and we will start with the first session.
Hello, everyone. Good morning. Buenos días a todos. We'll start now session 1 on solar, wind, marine, geothermal energy and storage. So we have 10 minutes for the presentation, Q&A, and then a couple of minutes to switch to the next speaker. So, okay, we will start now with our first speaker, Dr. Osvaldo Rodriguez Hernandez from the Institute of Renewable Energy, discussing about research about the institution in UNAM. Please. Dr. Rodriguez.
Yes, thank you, Dr. Leonardo. Can you hear me? Can you see my screen, my presentation in full screen? Okay. Thank you. Thank you very much. So, yes, thank you for the invitation. Thank you for the presentation. My name is Osvaldo Rodriguez, and I am responsible of the Wind Energy Group Laboratory at the UNAM. So, there is my email. I will present it also at the end of the presentation. So I have this challenge to introduce what we've been doing in research regarding wind energy. And so how did we choose to introduce this presentation to start to present these research lines? Basically, we present research that we have experience, that we have laboratory infrastructure. We have also research lines that has international collaboration, and I think that the most important is that we have students. The students from undergrad and grad students at the area of engineering, renewable energy engineering or energy engineering. So the people that participate in this group essentially are 6 researchers. We collaborate in this area. We are 3 physicists and 3 electrical engineers, and we will see why is composed in this way, this group. So the first research line is related with wind resource assessment or the wind resource modeling. In the right side of this slide, in the upper part of this slide, we can see reanalysis data. So what we've been doing is to study how reliable these meteorological products or these meteorological simulations are to reproduce wind conditions. We've been this research is we've been using these simulations to analyze how the wind resource is behaved, and we've been increasing the resolution, spatial resolution, to understand the wind behavior. So we can watch 2 examples. The first one is using reanalysis data, that is a global modeling of the wind resource. And the second one is a mesoscale modeling that we've been modeling at the institute. And this mesoscale modeling, it helps us to understand how the wind behaves. And the next step that we would like to do is to improve resolution. At the level to understand how the wind turbine interacts with the environment, or how a wind farm interacts with the environment. To do, well, these 2 simulations were done by 2 PhD students of the group, Gustavo and Diego. And we complement, I think that a proper way to improve the resolution of this kind of problems is to using computational fluid dynamics. It's also one of the research areas that we have experience. These CFD simulations, we have the ability to make our own codes, and also to use these tools as the open form simulations. But I think that the most important that to have this ability to make simulations is to complement it with the experimental with experimentation. So we've been working in this wind tunnel, into which we will integrating a particle image velocimetry to test it in this wind tunnel that is in the ER facilities. We are in 1.2 we are finishing to integrate this wind tunnel, and the idea is to test to polish this PIV skills that we already have in water, to translate this into air, and also to use infrastructure that is available at the university, that is a larger wind tunnel that is at the Mexico City University. So all these works is the design of this wind tunnel, this work of David Roberto Dominguez. And so this is a perspective of how we can analyze wind assessment. A different perspective that is also studied at the group is data science. So use this machine learning, very actual tools that are available to understand how the wind behaves and relay that behavior with the power production. So we can, here is defined a concept of a state of wind. It's this state of wind is decided by or defined by an algorithm. This algorithm is related with wind power production. This is oriented to make algorithms to improve the understanding of how the wind behaves and to implement these control algorithms in wind farms. Now, the power electronics. Power electronics is also a research area. So this area is also not only focused on wind turbines, it's focused also in the PV. So how to integrate these two sources of variable sources of energy without disturbing the electrical grid. This is the main goal of this. So we have the ability in the laboratory to modeling, to design, to simulate, and to implement these designs, these two fields of energy, how to condition it, the energy and the interconnection. And these two, mainly in these two areas on solar, wind energy, and storage. Also, the last perspective that we tackle in the group of the wind energy research is how the integration of large amounts of wind turbines affect or not the electrical grid, or even how this electrical grid should evolve to reach this goal of larger amounts of variable energy. So to preserve this technical characteristic of regulating voltage or frequency, and we need to understand how this collective of this large amount of energy can be integrated into the electrical grid. So the goal is to develop these solutions to improve the management and oriented to this near future that well, we expect a near future with larger penetration of renewable sources of energy. And that's my last slide. I think that we are on time. Thank you very much for your attention.
Thank you very much, Dr. Rodriguez, Professor Rodriguez. And we have a couple of minutes for questions. If you have, you can unmute if you want to ask the question, or do it in the chat. I will do one question, Osvaldo.
Yes.
The simulations are at what scale are you the work, the program, the software? Are you doing regional? Are you doing a boundary layer scale, or what are the
in the work simulations?
Those simulations are
okay. The first one, the upper one, are reanalysis data. So this is information that is available from NASA or ECMWF institutions, and we used to analyze regional behavior. In this specific case, we were trying to understand how tropical cyclones affects wind turbine in a specific location, and then we use this tool to identify this time series of the wind speed, and to extract them. The second one is a WRF simulation. It's a mesoscale. The resolution of this one uses boundary conditions from the reanalysis data. We use that to make these simulations. We improve the resolution. The resolution of the lower simulation is 1 kilometer per 1 kilometer, and the upper one is from 30 kilometers, if I remember right. So the idea is to improve this resolution, and at the same time understand how good or how reliable these tools are to understand the wind behavior. In some regions in Mexico, by example, one of our results is that reanalysis data behaves pretty good, and in some of the other ones, we need to make these higher resolutions.
Perfect. Thank you. Very quick. We don't have much time, but Luis Mejia is asking, is Mexico already using wind energy?
Yeah, we are using. We have an installed capacity. I think that in the Istmus of the Tehuantepec, I think that the 5% of the electrical wind energy contributes to the 5% of the electric generation. So yes, we have. I think that the facilities are mainly focused or installed in the Tamaulipas, that is in the north of Mexico, in the Oaxaca, that is in the Tehuantepec Isthmus, and some central regions of Mexico, and Tijuana, this region of La Rumorosa. So yes, we have.
Perfect. Thank you. Okay, we are going to now move to the next speaker, which is me.
Let me just say briefly, Dr. Leonardo Chamorro is an outstanding researcher at the University of Illinois. We are very proud of all his accomplishments. He belongs to the Department of Mechanical Science and Engineering at the University of Illinois in Urbana-Champaign. Thank you, Dr. Chamorro, for putting this program together.
Thank you. Thank you, Elvira. I will try. Let's see if it works. Can you see the presentation?
Not yet. Yeah, now it's there, but it's the opposite. We can see
yeah.
Uh-huh.
1 second. It's working strange, my computer. 1 second, please. Let me open. Sorry. Let me share the screen again. These things happen.
I have your presentation ready. If you want, I can share it.
Yes.
Do you want me to share it?
Yes, please.
There you go. It's there.
Okay, perfect. So I wanted to discuss a couple of important points in the wind turbines and wind farms. Is related to what the previous speaker was talking about, the influence of wind and steadiness on the power fluctuations at level of single wind turbines and collective behaviors of wind farm. This is extremely relevant because characterizing those provides insight for the people managing operators of the wind turbines. So okay, so let's continue. Okay, so very briefly about our group. So we are we do theory and experiments, experimental work that at different Reynolds number, ranging from microscale to hundreds of thousands. And then one of those research area is wind turbine. So, okay, thank you.
So when we tackle the problem of power fluctuations and mean power and power fluctuations, we have to account for the variability of the wind. That is central. And in that, we need somehow to represent the turbine as a body, black box, that eventually we wanted to find a certain transfer function that we input the wind with the convolute with the transfer function, and then we get power output. That's a basic idea. So we pick the unsteady equation of the wind, wind energy turbine, and then we just solve the equation considering the variability, the spectrum of the wind, the incoming wind, the impinging wind to the rotor. Okay, so by doing that, and then I will leave some references so you can see that, or you can ask me later. It is possible to uncover that transfer function representing the turbine structure, and the transfer function, as we see here, depends for relatively large frequencies. It has a scaling of frequency to -2, to the power of -2. So if you convolute this with incoming wind, you can get the spectral behavior of the power output fluctuations. Actually, if we test this concept with the laboratory units, measurements of the wind and power and field scales, wind and power, we can compare that behavior. And then if we move, and then here it is one representative example of what I'm talking about. The red, the spectral, this is a spectral distribution at different frequency of the fluctuations. The red one represents the incoming wind. It's very standard, well-known, sort of universal behavior of the power spectrum. And then in the curve there, blue curve, is the transfer function, this tuning-free fundamental theoretical transfer function. And then at the bottom, the black is the result, the measured power output fluctuations. And then if you see from here, you see that the power output fluctuations has different regions. One is in the lower frequency region has a scaling behavior of f-2 that follows the transfer function that we are talking about. But in the higher frequency region follows a scaling law of -5 ser -2, which is a convolution between the Kolmogorov, from the Kolmogorov scaling from the wind and the transfer function, and this was measured. So this really the simple fundamental equation follows that. So now we would like to test this at different scale, laboratory scale to full scale wind turbines, and then you see the blue and black curves represent the tuning free formulation and measure. And then you can see there that we can predict the variability, the structure of the power fluctuations. And then the equation I'm putting up there is our transfer function with a well-known velocity spectrum that could be von Karman and Keimal models. And then this is the case when you even don't have information about wind. Even with basic information, you can get what would be the power fluctuations of a wind turbine if you put it in a given place. So it's a pretty robust, pretty powerful tool that people can use in electrical engineering, mechanical engineering, structural engineering, civil engineering. Now, if we move to the collective behavior of power fluctuation of wind at level of wind farms, now we have to integrate this formulation into considering the communication between the turbines. Okay. And then this is just measure. This is just, let's inspect first. If we see for instance, the first row of turbine, the A plot, we see that the red again is the wind, incoming wind, and the black is the variability, the spectrum of the power output fluctuations. And then we see the scaling. Then the fourth row of the turbines, we see sort of the same scaling, and the seventh row is the same scaling. So this motivates us to see that it's possible to find this fundamental formulation that describe the collective behavior of wind farms. Okay, so I will leave a reference, but using the properties of the variance fluctuations in real space, as we all know, and some of the fundamental turbulence Krishnan random sweeping hypothesis, and then moving this into Fourier space, and manipulating those concepts with the unsteady energy equation of the wind turbines, we can analytically find what is phi p at the bottom, phi p, which is a spectrum of the power output of the wind farm, which is represent the sum, the contribution of the first term, all the individual turbines, plus the cross communication, the cross covariance between different units within the wind farm. Those two represent. Looks messy, but it's conceptually simple. And then now what I'm showing here is just apply for this laboratory scale, just the measure, just direct measurement. The black curve is the measured power output, collective power output of the wind farm, and the red is the model. Tuning free, no parameter tweaking here, is just direct application of the formulation. So what is this telling? Is a pretty decent, the formulation does a pretty decent job, and then tells that we can, knowing the incoming characteristic of the flow, then we can predict what is the collective behavior of the wind farm. And this opens many possibilities for operation, design, and so on, as we discussed, at different level of engineering. And then here, final remarks then. So we have for the community a tuning-free model that describe the power output fluctuation for wind turbines and wind farms. And then we have found that the power output actually exhibit scaling -5 SER, -2. The -5 SER is from Kolmogorov, the wind energy scaling, and the -2 represent the structure of the turbine, the turbine itself. And then I leave at there some our reference from my group that describe in detail how we derive these expressions. Thank you.
Thank you, Dr. Chamorro. We continue with the program. Or if you have questions, please write them in the chat. Preguntas para el Dr. Chamorro. Sí, Marina, puede abrir. Sí, adelante.
Hi, when you're talking about you have data from all these experimental turbines, are you talking about simulation, or do you really have a physical space for a collection of this turbine?
So thank you. Yes, we did experiments in the wind tunnel, but also at very small scale in the field with 3 meters wind turbines. But we have another paper also that proves that even at this low Reynolds number in the wind tunnel, we have demonstrated that they are representative of full scale.
Okay, but do you have a facility that has like...
Oh, yes, sorry, yes. So, we have wind tunnel, we have small field turbines, and then we have the instrumentation also to measure flow and power output, yeah.
How big is this facility? I'm talking about the small turbines.
Oh, yes,
you get your experimental data. How big is that?
No, the turbines in the wind tunnel are very, very small. The diameter is on the order of 12.5 centimeters.
Okay, so you are talking about experimentation between a wind. Okay,
correct.
Thank you.
Hi, Neil.
Hey.
This and very nice presentation. Thanks. I want to ask, have you ever done anything related to vertical axis wind turbines?
Just a little bit, not much. My focus has been done in the horizontal, but yes, it's in the radar.
Okay, so do you think, I mean, the findings you got from a horizontal axis still hold for vertical axis?
Oh yes, it's fundamentally is similar. Absolutely.
Okay.
There's different drag coefficient, different, right? The thrust coefficient is slightly different, but all the fundamentals, all the framework is the same, exactly.
Okay, great. Thank you.
One question from Eduardo Ramos. How does your model relate to a Fourier low-pass filter?
So we have demonstrated that that a small scale smaller than the rotor diameter doesn't affect the power output fluctuations. So you can filter those out. We have a paper on that also. The small scale doesn't affect, as you can imagine, intuition tells you also that the small scale doesn't affect the power output fluctuations. You can filter it out. So you have to focus only on those larger scales.
Very good. Any other last question? No more questions? I guess there is one more question. Have you done some research on wind gas and its effect?
Yes, I have done. We can discuss after the presentation. Those wind gas has a big impact on the loading and the power output spectrum behavior, and they can last within the wind farm. Of course, deep in the farm, those effects vanish, but they are very strong. Also, not only gas, but also low-level jets that I think in Mexico you have in several areas, and those are pretty scary natural phenomenon.
Thank you very much, Leo Chamorro. Now you can continue with the program. Thank you.
Yes. Okay. So let's move on to our third speaker is Professor Rodolfo Silva that will discuss about progress and challenge of the Mexican Center of Innovation in Ocean Engineering. Professor Silva.
Hello, good morning. I am trying out. Thank you for the invitation. I hope you can see now my presentation. Well, I would like to give a brief explanation what we are doing here at the Institute of Engineering. I am the responsible of a very large group. In this group, we are working around 40 Mexican institutions and more, and we have collaboration with more than 15 international bodies. In this group, we are working around 800 persons, around 200 researchers, and the rest are especially mainly students. We are organized like in a mesh. We have in this grid several groups that are working directly on some topics. For example, our main topics are the source evaluation, but also at the same time we are working with environmental assessment, social topics, network integration, material subsystem, numerical model, physical modeling, and we have this kind of large and small scale modeling. Also, we have some groups that are working directly with the diffusion and dissemination of the result that we have. We have also a business unit, and in this part, we are also working very dynamically with the technology roadmap. One of the things that we already have is the power availability in Mexico. Our main topics are essentially ocean currents, thermal gradient, wave, and also salinity gradient. In this part, we are working as a cross-cutting groups. Also, for example, developing some technologies we are testing in a small scale, medium, and large scale facilities among numerical modeling. Also, we are, for example, especially working in this case, I am showing some result with some small scale modeling here at the Institute of Engineering, but also with part of the international collaboration. We are testing, for example, this vertical turbine in a larger scale in Scotland. Also, we are working in labs and also numerical modeling with some devices in order to try to use the wave as an energy resource. Also, we have a lot of interest with the salinity gradient that I think is a very open area to have research, because at the same time we have produced energy, clean, fresh water, and also we are using, in this case, this kind of, for example, membrane that we are developing to see what are the behaviors of them in order to improve the water quality in coastal area. We have in one of the universities that is in our network, we have, for example, now some facilities for OTEC, for observe thermal gradient. One of the things that for us is quite important, because there is a very large lack of information in Mexico. We are running very frequent some field work. In fact, we use our oceanographic cruiser that we have through the university, and also we have now 3 natural labs. One of them is in Ensenada, the other one is in Manzanillo, and the most important is in the Caribbean Sea. Partially is in Marine Science Institute in Puerto Morelos, but also we have some equipment in Cozumel. Other thing that for us is very important is the impact assessment. We are working very, very hard, and together with some biologists, in fact, we are working with mammals and other kind of species, and we have a lot of information now that we are trying to use. And also we have a new criteria. In fact, we are working very, very close to the OS, that is the Ocean Energy System, that is part of the International Energy Agency. That, in fact, I am part of that group, together in order to try to provide clean energy and not only renewable energy. That is part of the thing that we are doing with the materials. In the materials, we are working with new material, but also we are working, for example, trying to characterize the biofouling in some places, because we have another kind of properties in marine waters in Mexico. It's a tropical area, and the behavior of the materials are very different. That is trying to show in 10 minutes what we are doing in this group. And thank you very much again for the information. And if you have any question, you can ask me now, or if you prefer, you can send me an email. Thank you very much.
Thank you very much for the presentation. Very nice. Questions?
Well, more than a question, a congratulations, Dr. Silva, to you and your group. We really hope we can collaborate in the very near future. Thank you.
Thank you very much. In this group, in fact, there are some people that now they are presenting part of their research area, and they are part of this group. We are people from the social science to the technology areas, and also there are many people between these areas.
Okay, perfect. Thank you again, Professor Silva.
Thank you.
We move to the next speaker is Professor Jinhui Jan at Civil Engineering here at UAUC, that will discuss about modeling of tidal turbines. Jinhui?
Okay, great. Neil, thank you very much. So hello, everyone. It's my pleasure to be here. Actually, I recorded the presentation, so let me share my screen and then play the video. And after that, I can answer your questions. Thank you very much. So just 1 second. Good morning, everyone. My name is Jinghui Yan. I'm assistant professor in civil and environmental engineering at the University of Illinois, Urbana-Champaign. Thank you very much for the invitation. It is my great pleasure to present in this symposium. So in this presentation, I will talk about free surface flow modeling of tidal turbines. So let me begin with some background about the current status of tidal energy in the United States. Some of you may know United States has a huge potential in tidal energy. Here I extracted some statistics from Department of Energy. First of all, the length of US coastline is around 32,000 kilometers. Each year, the average tidal and wave energy is about 21,000 terawatt hours. If we only harness 20% of this amount with a 50% conversion efficiency, we would be able to provide 70% of total US electricity consumption each year. So it is really promising. As a result, tidal energy is attracting a lot of attention in the United States. Here I show you a tidal farm in New York East River deployed by Vandenberg Power. In order to better design the tidal turbine structure and to optimize the tidal farm efficiency, numerical simulations, especially CFD simulations, are playing an essential role. However, if you look at the literature, you will see that most of the current numerical simulations still focus on pure hydrodynamic simulation without considering the free surface effect. Although many experiments has indicated that free surface can be very important. So in our group, we are trying to develop some numerical methods that can simulate tidal turbines in free surface flow and quantify their effect. Our approach is based on level set method. Here you see air, water to fluid domain, and at each point of this domain, we defined a level set function, which is the side distance function from this point to the air-water interface. With the level set function, you can define a heaven set function. With the heaven set function, you can evaluate the fluid density and the fluid viscosity by the linear interpolation between the air phase and the water phase. Once you have the fluid properties, you can start to write down the governing equations for free surface flow. So you first have the two-phase Navier-Stokes equation of incompressible flow. So here the Navier-Stokes equation are written in arbitrary Lagrangian O'Nearian framework because the turbine is rotating and we want to simulate flow around moving domains with moving interface. In this case, arbitrary Lagrangian O'Nearian probably is the best way to go. And for the Navier-Stokes field, it is governed by the pure convection. It's governed by a pure convection equation, which is also written in ELE description. So here, Navier-Stokes equation plus Navier-Stokes convection equation are the governing equation of free surface flow at a continuous level. And then the question is how to solve them. Because of the limited time, I couldn't go through all the details. Here I summarize the key numerical methods that are used in our framework. So we use variational multi-scale formulation as a large eddy simulation model. We include redistancing and mass rebalancing to enhance the performance of the Navier-Stokes method. And we use generalized method for time integration. And then the velocity, pressure, and the Navier-Stokes field are solved in a fully coupled fashion with GMRS as the linear solver. So with this framework, let me demonstrate how we use it to investigate the free surface effect on tidal turbine performance. We first simulate a single tidal turbine using uniform inflow condition. We performed both pure hydrodynamic simulation without free surface and the free surface simulations with deep immersion depths. One is very shallow and one is very deep. Here is the most important result. Those two plots shows you the time history of the thrust coefficient and the power coefficient. There are three important messages I want to say. First of all, free surface calculation agree very well with the experimental measurement for both shallow immersion case and the deep immersion case. Secondly, pure hydrodynamic simulation is not accurate. If you immerse the turbine very deep, it is okay, because in this case, the turbine barely feels the presence of free surface. However, if you place the turbine closer to the free surface, you can clearly see the error of a pure hydrodynamic simulation. Thirdly, the performance of a tidal turbine is better in deep immersion case under this uniform inflow condition. Instead of using uniform inflow, you can put some waves. So this is a free surface simulation of a single turbine using airway wave inflow condition. And you can see here, when you have waves, the flow behavior is much more complicated. Let me replay the video. The flow behavior is more complicated. You clearly see the interaction between free surface and the tip vortex generated by the rotating tower. Because you have waves, you will see fluctuations in the thrust and the power coefficients. However, if you average those coefficients in the fully developed stage, you still see that as you place the turbine closer to the free surface, both power coefficient and the thrust coefficient decrease. This means in those idealized inflow conditions, free surface has a negative effect on the tidal turbine performance. This sounds like a common sense conclusion, but my key point is you need to quantify the effect. And most importantly, if you have a realistic wave condition, in order to quantify the free surface effect, you have to perform the simulation by explicitly model the free surface. Now with the formulation, you can also simulate multiple turbines in free surface flow. And in this case, you can investigate the combined effect of both free surface and the wake. And here I show you a case study of two back-to-back tidal turbines in free surface flow using uniform inflow condition. The immersion depth we use here is based on the deep immersion depth from the single turbine configuration. From the single turbine configuration, we found out the free surface is not important. Now we have two turbines and we want to know whether it is still the case or not. So in order to figure this out, we also performed both free surface flow simulation and a pure hydrodynamic simulation in order to do the comparison. Now, first, let's look at the wake effect. So those two plots shows you the time history of thrust and the power coefficient from the free surface flow simulation. As you can see here, for the upstream turbine, the coefficients still agree with the coefficients of a single turbine configuration. But if you look at the downstream turbine, you see significant drop for both thrust coefficient and the power coefficient. And you will see this more clearly from this slide. This slide shows you the time average water speed at different locations between downstream turbine and the upstream turbine. And as you can see here, right after the upstream turbine, the uniform profile is immediately distorted. And as you go downstream, at each radius coordinates, the water speed is becoming smaller and smaller because a lot of kinetic energy is already distracted by the upstream turbine. As a result, you see the significant drop of the efficiency of the downstream turbine. And if you look at the comparison of the free surface simulation and the hydrodynamic simulation, you see that hydrodynamic simulation overpredict the water speed almost at every location. Now we will do a more careful study between the free surface simulation and the hydrodynamic simulation to investigate the free surface effect. So those two plots and this table shows you the thrust coefficient and the power coefficient at the fully developable stage for both upstream turbine and the downstream turbine. And then you can see here we did the comparison between free surface flow simulation and the pure hydrodynamic simulation. If you look at the upstream turbine, you see both free surface simulation and the pure hydrodynamic simulation agree very well, which means in this two back-to-back turbine configuration, free surface effect is still not important for the upstream turbine. However, if you look at the downstream turbine, you see that hydrodynamic simulation predict bigger coefficient for the thrust coefficient and the power coefficient. So which means, although the free surface is not important for the upstream turbine, but it affects the downstream turbine performance, right? Performance, and it has a negative effect. And this is not surprising if you look at a snapshot of the simulation. You see very large deformation of the free surface flow, right? For free surface. And because of the complicated interaction between free surface and the wake, and of course, in the end, it will have a big influence on the downstream turbine performance. Now, let me draw some conclusive remarks. So as I said, free surface effect is very important in tidal turbine modeling. And to quantify the free surface effect, we have developed a validated computational free surface flow simulation. And we have applied it to both single turbine configuration and the multiple turbine configuration. And you can use this framework to study the free surface effect and the wake effect. And this framework is very general, and you can apply it to other hydro energy problems. So with that, thank you for your attention, and I'm looking forward to your questions.
Thank you very much, Jing Hui. Very great talk. And unfortunately, we run into exactly 12 minutes. We have to switch to next speaker. So leave your message, so your questions there, and then we can follow up with Jing Hui. So now the next speaker is Professor Norma Lopez from UNAM that will discuss about geothermal energy in Mexico. Professor Lopez.
Thank you, Professor Chamorro. Good morning to everyone. Thank you for this kind invitation. You can see my presentation, right?
Yes.
Okay. Okay. I will talk about the energy geostructure, in particular, the direct use of shallow geothermal energy in Mexico. What about our research? Since 2017, the Instituto de Ingeniería has been a pioneer institution for the, for the promotion and development of energy geostructure in Mexico. Our research project includes three main topics. The first one is the numerical and analytical study of thermomechanical behavior of energy piles. For example, you can see here a numerical model that we use to perform numerical analysis of energy piles using the curve axis to determine. With this very simple model, we compute the temperature variation, and then we obtain the thermomechanical load, the variation with depth, and also the variation with time. We also develop analytical and numerical tools to study the thermal behavior of energy piles. In particular, we use the thermal load for an energy pile as a data in order to compute the average fluid temperature change using different analytical models. In addition, we have measured the Mexican soil thermal properties in both in laboratory and in situ tests. In particular, we use the first time the thermal needle proof method. We have used this equipment, the KD2 Pro, in both in laboratory tests and in field or in situ tests. And up to now, we have made effort to systematically characterize the thermal properties of Mexican soils. Up to now, we have measured the thermal properties in some states in Mexico. One of them are Tabasco, in Mexico City, of course, in the state of Mexico, in Nayarit, in Jalisco, in a few days. We'll start with this measure. You can see here some stratigraphic profiles and thermal properties that we have obtained. In this case, we have a very point measure. That's why we'll have the necessity to construct mobile equipment. This equipment is the first mobile equipment for thermal response test in Mexico. I'm sorry. We have a study also, in addition, for the thermal properties, the effect of the soil microstructural and mineralogical characteristics. You maybe know that Mexico City have very peculiar soils. In particular, the clayey soils, we have some microorganisms into the soil. For example, ostracods and diatomates. These microorganisms make that the soil has very particular characteristic and change the properties, of course, the thermal properties. Okay, with this equipment, this is the first mobile equipment for performed thermal response tests in Mexico. We have performed some tests in both into the borehole, into the soil, or on an energy pulse. This experience obtained has enabled us to perform feasibility studies, design and monitor the construction of the field project with energy geostructure in Mexico. Up to now, we have participated in several projects. The first of them is the Residence C73 in Mexico City. We have two test fields. One of them is in Mexico City and the next one is in Nayarit. And also in this moment, we are participating in one project that Puerto Vallarta International Airport has the necessity or the interest to construct energy piles in the foundation of this airport terminal. This terminal is in Puerto Vallarta in Jalisco, Mexico. This is some information important about the project of the Residence C73. The main characteristics are the following. You can see here a picture of this residence. This is our vanguardist private residence located on the northwestern hill in Mexico City. It's a one-story building supported on 15.5 board piles. In this foundation, we construct 6 energy piles equipped with 4 U-loop pipes connected in series. These energy piles were designed to provide heating to the resident main chamber during the winter. You can see here the foundation layout, and you can see here some pictures about the construction process of these energy piles. You can see here the pipe final configuration, some pressure tests that we need to perform, the reinforcer cage installation, and the concrete pour. In this case, in one of these energy piles, we perform a thermal response test. You can see here some pictures about this test. Another project is that I can mention, the Terminal T2 in Puerto Vallarta. The main characteristic is a new terminal located on the Pacific coast in Jalisco in the western of Mexico. This is the major beach resort city with tropical wet dry climate. It's a two-story building supported on 48 board piles and barrel. The feasibility state allows all to a preliminary thermal design to perform at the preliminary thermal designs and prepare a TRT that in this moment is in process. We hope that we start this test in a few days. This is the cross section of the energy pile that we construct, as you can see here in this photograph. We construct one prototype energy pile in order to perform this thermal response test. With this test, we'll expect to obtain the thermal properties in order to perform a back analysis about the preliminary thermal design that we make before. You can see here the thermal law that we use to perform this analysis. You can see here a photograph and a perspective of this terminal. One another project is in order to start also in a few, I think in 1 month more. We have here a test field in Nayarit in Mexico. This test field is located in the geothermal field named Nayarit Dome at the San Pedro Lagunillas in the western of Mexico. We have here the first thermal response test we intend to carry it out in ground and water field borehole in the country. We are in the planning stage. We are defining the characteristic of the borehole and the TRT duration and the procedure to perform this test. You can see here a geological map of this study zone and a view of this place. This is the photograph of the that will hope to perform this this test. And that's it all very, very fast. If you have some question, please tell me now.
Thank you very much, Professor. Yes, we have 1 minute for questions. No questions? Okay,
Well,
thank you very much, Elvira.
No, I just want to congratulate Professor Norma Patricia Lopez Acosta for a very, very impressive work. We're very proud to be Mexicans.
Thank you very much, Professor Elvira.
Yes, I echo the congratulations. Very, very nice. Very, yes, very, very difficult, very challenging, and very promising work, Professor Lopez. Okay, so we move to our next speaker, Professor Roman Makenkov from UIUC, that will follow up on some discussion on geothermal systems. Roman.
Hello, I still cannot share my screen. Can I be allowed to do that? Okay, now it's working. Thank you. So are you able to see that?
Yes.
Okay, just a second. Okay, so you see my slides, right? Fantastic. So I will start introducing enhanced geothermal systems. And this is, so we're going deeper than what was just discussed. And of course, the motivation is producing renewable energy, decreasing the amount of CO2 emissions. You know that when we are heating our buildings, when we're trying to produce energy for any kind of purposes, there are a lot of greenhouse gas emissions that are associated with that. US is the country that is unfortunately leading this in terms of emissions per person. There are a number of ways what we can do. The one that I wanted to focus on today is geothermal, but deep geothermal energy. For the big report that we had back 5 years ago, renewable energy in the US energy consumption was contributing just to 11% of the overall, and out of the whole sources of renewable, geothermal was just 2%. It's growing a little bit now, but I think we can do much better. And I know that the previous speaker did show us some shallow geothermal systems. I'm going to introduce enhanced geothermal systems and then talk a little bit about our research in this area. I'm purposefully not showing a similar map for Mexico because I think the next speaker will be talking about geothermal projects in Mexico. So, but basically the idea is the following, that when we start going deeper underground, the rock is getting hotter. The average geothermal gradient is around 25 degrees Celsius per kilometer. Here in Illinois, we know very well first 2 kilometers. We know that at the depth of 2 kilometers, we have around 70 degrees Celsius, around 10 degrees on the surface. However, there are places where this gradient is much higher. Everybody probably knows about Iceland, where you can have actually hot water coming to the surface. And we also have in the US, especially Western states, Idaho, Utah, Oregon, we have also very high geothermal gradients. And what that means is that we can actually go underground to a depth of few kilometers, 3, 4, 5 kilometers. We can find the formation when the rock is already hot, more than 100, 150 degrees. And what we can do is then to try to extract the energy from this hot rock. The way how it's usually done is that either we can use the conventional system where in the hot rock you obviously have hot fluid. We can pump this fluid out, and then we can either use it for heating buildings or producing water, steam, and hence producing energy. However, what is being now developed, and this system that actually can be used in a lot of locations, is called enhanced geothermal system, where you need to force the fluid to come out of the hot rock. And what you do for this purpose, you inject cold water, you fracture the rock, and then you have the injection well, and then you can have a number of production wells where you will be receiving hot water and then bringing it to the surface. Again, if it's not too hot, you can use it for heating purposes. If it's very hot, you can use it for producing water, steam, and energy. So I'm focusing on the second method because we can actually, I mean, there's a hot rock everywhere. It just depends on the depth where you go. And of course, another important thing here is that you actually need to find the proper formation where the fluid will be traveling over a certain period of time such that it has enough time to heat up, but at the same time, it's not ridiculously slow, so the material should still be permeable. And to do that, you need to create a network of fractures, and then we can use the technology that is being known for more than 100 years, but has a huge development over the last 25 years, which is called hydraulic fracturing, where we pump the fluid into usually a low permeable formation. In the US, we do that with shales. We create a network of fractures. And in the case of geothermal energy production, we need to make sure that if we have at least 2 networks, that they are joined, right, from the injection well and from the production well. And that means that we actually need to know the rock properties very well as being able to predict what's going to happen when we inject fluid in the rock. And the problem actually is multi-scale in a way that fracturing of rock is the process that we can try to explain from the macroscopic point of view, where we say that the material is reaching its tensile strength. But we also know that actually these processes are governed by microscale processes. It's the initiation of fractures and propagation of fractures inside the material that are determined by the stress discontinuities on a very small scale. So we need to kind of join these two scales to really understand, under the conditions that we have underground, which is high temperature, very high compressive stresses, and certain, of course, fluid pressures, can we predict when these fractures will start propagating? And this is one of the things that we're doing in the rock mechanics lab at the University of Illinois. So we have a bunch of high pressure equipment, and some of our equipment can actually work at high temperatures as well, up to 150 degrees. So that would be representative of a geothermal system. So we can work with different fluids, oil, water, CO2, and we can test the material properties as well as actually to simulate the conditions where we create fractures in the rock. So the setup, one of the setups that we're developing and working on is the setup for hydraulic fracturing, where we use the block of rock. Here it's granite. We can instrument it with the devices that measure its deformation, that can also send seismic waves through it. And we then create a borehole, and we create a fracture, and we try to monitor when it's initiating and how it is propagating. And we have been able to actually develop some tools to really see where the fracture tip is going, at which pressure the fracture is initiating. And now the system that we use to monitor fractures, because of course you cannot see through this when this rock is subjected to high stresses, right? You cannot see through it. It's granite, as you can see on the figure on the right. But we do have this acoustic system that, we send in a number of waves through the material, and we can actually capture when this fracture is start propagating and then deflecting and reflecting the signals that we're sending. And we have a very good match between our seismic ultrasonic measurements and then the measurements of the crack path that we have after we cut the specimen. Another thing is, of course, addressing, okay, if we created a fracture in the material, how can we control how much fluid flows through it? Because this is a critical question for geothermal energy production. So we are trying to test the rock that either we have created already some fracture, or it was fractured naturally. So this material comes from a depth of more than 2 kilometers here in Illinois. It's very stiff and dense crystalline rock, rhyolite, very small porosity. So the main flow, of course, happens through the fractures. And what we try to address is that depending on the state of stress and the temperature, and the injection rates, how the permeability, the ability of the material to permeate fluid will change. And we see that it's actually a critical thing, the amount of loading that you apply and the way how the fracture is actually displaced so how much it is open basically will change the amount of fluid that can flow through this fractured material by a few orders of magnitude. So this is another important thing to keep in mind. The third question that we're looking at is related to size effect, because whatever we can test in the lab, it will have, we can only extrapolate these rules to the maximum specimen that we tested was 1 meter long. And of course, when we go to the field, those will be tens or hundreds of meters. So we want to develop some size effect loss, some upscaling loss to be able to predict, okay, if at these conditions, the fracture is propagating, under this loading, what will happen in the field? So we look at this size effect, trying to develop some constitutive relationship and actually monitor where the fracture starts propagating and how it's affecting the rock around it. So we use some optical methods, digital image correlation to track the fracture propagation, and we use acoustic emission, the method that allows us to monitor how this field of microcracks is actually traveling along with the fracture. And finally, of course, I didn't mention it explicitly, but with one of the issues with enhanced geothermal systems is that every time you start disturbing the rock underground, you know that we have earthquakes happening without human influence, right? But also what the phenomenon that is called induced seismicity, where when we start doing something, some human activity, not necessarily underground, but in our case, injecting fluid, there is a high chance that you can actually produce earthquakes, and that was happening in a few cases. There were a few cases in Europe. There was a recent case in Korea, and that means that we also need to address the strength properties and actually when the material is going to start producing those seismic events. So we also look at this kind of behavior for crystalline rock, trying to simulate the conditions. Again, it's important that the rock is hot, the rock is subjected to high confining pressures, because we know that this behavior is stress and temperature dependent. So my kind of summary is that there are a few things that we designated will be important for this, for properly addressing the behavior of enhanced geothermal systems. We're currently not, there is an idea of making like a pilot project here in Illinois at a depth of two something kilometers. But so far we were mainly focusing on the modeling and laboratory testing to address those issues. And there's some other things, as like the test that I showed, we still haven't gotten to high temperature. And also we would at a certain point need to simulate the chemistry of the pore fluid, because that is also one of the issues in these enhanced geothermal systems. But those things that are associated with fracture propagation at different scales, monitoring of fractures, and inducing small earthquakes, this is what we are focusing on, and we'll be happy to discuss and collaborate. Thank you.
Thank you, Roman. We ran out of time.
Sorry.
No problem. You always ask 40 seconds, but it's okay. Okay, let's move on to the next speaker. Is Professor Edgar Santoyo from the Institute of Renewable Energy at UNAM, and we'll continue discussing about geothermal energy. Professor Santoyo?
Yeah, thank you very much. Just let me try to share my presentation. Okay. Can you see the slide? Yeah. Okay.
Yes.
Good morning, everybody. Thank you very much to all the organizers for the kind invitation to participate in this symposium and a good collaboration initiative between Illinois University and UNAM. This presentation won't be a technical exposition, but rather a very brief talk about the research areas on geothermal energy that are currently conducted by the Bioenergy Research Group of the Institute for Renewable Energy. The agenda that has been prepared for this talk will include some aspects of the potential use of geothermal energy in Mexico, the current and the future scenarios, some aspects, the research framework of program that are conducted with the goal to make an intersection with the prospection and exploitation of geothermal systems. And finally, I will give a very brief description of the research experiences and program, the infrastructure facilities, the team integration, some academic alliances and collaborations, and some bibliometric data of the GRG productivity. Finally, I will give a very description of the experiences on thesis and dissertation supervisions and teaching experiences. As you probably know, geothermal energy is a renewable energy that it's currently used in the world for the generation of electricity and other direct uses. In the context of power generation, the current installed capacity in the world is about 16 gigawatts, where the top geothermal countries are represented in the slide. As you can see, USA and Mexico are ranked in the first and sixth places regarding these geoenergy resources. I don't give more details about the type of geothermal system, but most of the commercial projects are related to the exploitation of geothermal systems, mainly the convective of hydrothermal system. The other type of system was already described in detail by the previous speaker, but it is related to the conductive hot dry rock systems, which are also referred as enhanced geothermal systems. As Mexico has an enormous amount of geothermal reserves, you can see in the slide that this enormous amount has been enabled to be estimated proven and probable possible reserves, which are given in the slide. Considering this enormous geoenergy amount of resource, in Mexico currently, there are 5 geothermal systems currently under exploitation: Cerro Prieto, Las Tres Vírgenes, the Domo de San Pedro, Los Azufres, and Los Sumeros. In addition to these geothermal fields, we have a large number of hydrothermal systems that are at present under exploration, including, in this case, the promissory zone of Acapulco, which was recently identified as a potential hot dry rock project for future exploitations. The upstream resource development of commercial geothermal project has been identified as the high risk and high cost barrier. And this mainly caused by the geothermal prospection and the well drilling stages. As a result of this analysis, several global research goals and challenges has been identified. Among these goals is stand out the development of new G-cube methodologies and tools for the geothermal prospection, a numerical method for the study of geothermal well drilling process, and to carry out water-rock interaction experiments for studying the scaling problems in geothermal plants, among other important researches. As a part of this global research work, it is very clear that accurate knowledge of some technical parameters is crucial for the prospection and exploitation of geothermal resources. Among these parameters are the temperature and pressure, the thermophysical and transport properties of the rock formation, the chemical characterization of geothermal fluid and rock samples, and the petrophysical properties. All these studies have been taken into account for the Geoenergy Research Group to carry out a comprehensive research program, which is based on the development of new and innovative G-cube methodology for a better, reliable prospection of hydrothermal systems and hot dry rock systems. More specifically, the GRG is working on several types of investigation, among which stand out the list of the studies that I am describing here. the new improved geothermometric tools for predicting deep equilibrium temperature with a better accuracy, new improved analytical methods based on heat transfer models for determining the static formation temperatures, which are very important to define the total amount of energy stored in geothermal system, mainly in the early exploration, as well as innovative geoanalytical methodology and instrument calibration based on geochemometrics practice for the correct chemical analysis of major and trace elements in fluids and rocks. Improved geoanalytical techniques, theoretical and experimental simulation of water-rock interaction processes for the calibration of solid geothermometers and the description of geochemical and mineralogical signatures. And there are another type of non-conventional investigation that we are conducted is innovative geochemical techniques for measuring gas emission in geothermal system and surrounding ecosystems, and high sensitivity geoanalytical techniques for the determination of baseline gas emission during the geothermal early exploration. And of course, some of these activities have been complemented by the application of artificial intelligence techniques for the solution of geothermal prospecting issues. The infrastructure facility that we have at the lab, we have sampling tools for the representative collection of fluid and rocks and rock sample preparation lab for chemical analysis. We have specialized laboratory based on analytical geochemistry, analysis of fluid inclusion in drilling cuttings and rock samples, soil gas detection, real-time sensing of gas emissions and hydrometeorological variables, water-rock interaction equipments, and we have also a computational modeling of process in geothermal system by using commercial and in-house developed software. Finally, and very recently, we have using computational software for carrying out the studies of life cycle assessment for the geothermal technology and other renewable energy systems. The Bioenergy Research Group is basically made up by five academic researchers, which we have, fortunately, the death of two of them, and the current structure is basically made up by 5 academic members, accompanied by a brilliant cloud of 14 graduate and undergraduate students, which are carrying out their thesis investigation. In the context of publication, around 300 articles have been published in a period of 26 years, which have a good impact among the world geoscientific community. Some bibliometric indicators that support this literature impact are shown in the slide. To provide an additional strength to the GRG research capacities, some alliances with other geothermal groups of Mexico have been established, among which stand out some institutions of the UNAM, such as there is a noise in the, well, such as the Center for Geosciences and the Institute of Geophysics and the Institute of Engineering of UNAM, and there are other institutions where we have very productive alliances. In relation to the academic collaboration carried out in research project and publication, around 300 national and international collaborations have been successfully carried out. Among these collaborations, a standout publication co-authored with researchers from several recognized institutions of Germany, India, Spain, USA and among other countries.
In time.
Yeah, just I want to close. In relation to the thesis and teaching experiences, a total of 60 works have been completed. And of course, we, with this very brief description of our capabilities, we are very happy and ready to start any collaboration with the Illinois University, either to carry out research projects or to promote the mobility of students. Thank you very much.
Okay, thank you very much, Professor Santoyo. Great talk. We will move, we don't have time now for questions. So we will move for the next speaker, Professor Joe Tom from the Civil Engineering Department at here, UIUC, that will discuss a related aspect of renewable energy foundations and cables. Joe?
Yes, sorry, let me try to share my screen here.
Yes.
Just having a bit of an issue. Okay, can you see that?
Yes.
Right, thanks. Thanks everyone for inviting me this morning. Great to see everyone virtually. I guess my talk is going to be a bit more high level. I'm going to talk specifically about one aspect of kind of development of offshore, in particular offshore renewable energy infrastructure, and that's scour hazard and what are the implications for design. So I sit in the Department of Civil and Environmental Engineering here at UIUC. So this comes from more the civil engineering infrastructure background side of things. Okay, so just offshore wind, focusing on offshore wind first. This has some application, as I saw in some of the earlier talks, to tidal energy and wave energy as well, but I guess most of the development offshore is offshore wind, so we'll focus on that. If we think about what happens in kind of offshore wind, we have the turbines offshore, and then we have cables that have to bring that power back to shore here, right? So there's geotechnical and scour aspects associated with all of this. In particular, in the US, we have a lot of onshore wind as well, but increasingly, well, I guess there is a recent development to move towards more offshore wind. The main reason for that is to get it away from people, right? People don't necessarily want or some people complain about it being in their backyard, but also there's more wind, there's cleaner wind offshore. So here's a map of the eastern part of the US. So basically the darker colors is higher wind speeds, and higher wind speeds equal more power. So you can see if we compare Illinois here around Champaign, we have decent amounts of wind, but even in the Great Lakes, there's a large amount, it's even faster, the wind. So if we look on the East Coast, there's a lot of fast wind there. And then moving down towards Mexico, we see the wind is reasonably fast. So that means there's potentially a lot of power that can be gained offshore. We can compare, for instance, around Virginia on the east coast of the US, where we've got this sort of purplish color. There's a similar sort of color around offshore Mexico. So I don't know that necessarily how much energy can be gained out of that, but there's some potential there. So that's kind of, as Professor Magninko talked about earlier, we're trying to move into more of a renewable kind of economies. And so offshore wind is a very focused part of that. So local scour, what are we talking about local scour? So we have infrastructure that's offshore to support the wind turbines that can take a variety of fashions. So it can be structures that are fixed to the seabed. They can be floating wind turbines, which are basically boats with the wind turbine on top, and they have to be anchored to the seabed. At any rate, there is some sort of connection between the structure and the seabed, which is made of soil. The idea of scour is when we have waves, we have currents in the ocean, so the water's moving. When the water moves around a structure that's on the seabed, that can lead to removal of the sediment from the local area. It's a complex phenomenon. We had some good pictures or some nice video earlier from Professor Yan about sort of the vortex dynamics and stuff that go on. We're not going to focus on that too much in this 10 minutes, but just to give you this idea, this is my background here. But to give you the idea, when the water moves, the sediment can move with it. If the sediment moves with it, that means that there can be a hole around the structure. So if we have our wind turbine, which is supported in this bottom right picture very commonly on what's called a monopile, which is a single cylinder that supports the structure. If there's a big hole around it, then we don't have that soil to support the structure anymore. And so the capacity of the foundation is gone. We know this happens very commonly in rivers. Nice well, not a nice picture for people on the train, but a common occurrence, one of the most common occurrences of bridge failure around the world is the flowing water in the river is going to lead to local scour. So a hole forms and then the capacity reduces. And so we get failure. Same thing can happen for offshore infrastructure and offshore energy. So just here's a video on the bottom left, just to give you an idea about scour and what that means. This was taken during my PhD in Australia. The idea here is as soon as we put a structure onto the seabed and we have a flow, in this case, coming from left to right, that can lead to sediment being transported away. If we looked very quickly at the beginning of that video, let me just go back and go forward. If we look very quickly at the beginning, the level of the seabed below that pipeline there reduces very quickly as the sediment starts to move, and then it starts to slow down after some time. So after some point, we have that initial fast rate of scour, so the seabed is lowering quickly, and then at some point it reaches what's called an equilibrium. In reality, it's not necessarily equilibrium. You can look at this picture here. We have a scour hole forming, and in the bottom, there's still some sediment moving around, right? They're sort of dancing around. It's a dancing type of equilibrium or a dynamic equilibrium rather than a completely static equilibrium. But at any rate, we get to some point where the scour depth stops. That soil has all gone. There's no longer that soil to resist the foundation, or to support the foundation rather. So if we talk about monopiles, what is basically going on? We can look at different research that people have done around the world. So this is focusing on a pile, which is this structure here on the left. If we push it sideways and we have a scour that's formed, then we get more movement. So when that wind is pushing on the wind turbine, it's pushing it sideways. If we have a scour hole that's formed, then it might move sideways, and that's a bad thing. Second thing that it does is, as we have a scour hole that forms, larger bending moments are created in the structure. This basically means the steel that's in the ground is being loaded more strongly, stronger. There's more loading acting on that steel, which is going to reduce its lifetime. It's going to lead to, if we allow the scour to occur and we're not preventing it from occur, that means we need bigger piles, we need more steel, and we need higher costs. It's already expensive to do construction offshore, and these turbines are very expensive. So if we're adding more cost to it, then that's going to limit the amount of development that we can do in pushing forward to our renewable energy goals. A lot of pictures here. Nice one here at the middle where we have a satellite image of an offshore wind farm in offshore UK. Right, the United Kingdom. So each of those white dots there is a wind turbine, and you can just see the plumes of soil which are being mobilized around each wind turbine and kind of moving away with the flow. So there's a lot of sediment being moved around in the cases where we don't have scour protection. So we know there's negative impacts. So what's normally done is that scour protection is done. So this on the right kind of illustrates that, where we have, basically we have to get a boat to come out there and drop big pieces of rock around that foundation. So that rock is much bigger, it's much heavier, and so when the currents come, it can't move. It's not as easily moved as the sand that's typically around the seabed, and so that provides a prevention or a mitigation of that scour occurrence. The problem is that's very expensive. So boats are expensive, right? That boat right there, it might cost at least $10,000 up to $100,000 a day. So that's a very expensive thing. So one estimate from Denmark is that if we think of the cost of a wind turbine, they may cost $1 million to $2 million per turbine. Don't quote me on that. That's just a general number. And the scour protection itself can be up to about $200,000 USD. So this is a big impact. This is a big cost driver for these offshore wind turbine developments. It's something to keep in mind, just to not forget about scour. One other thing that happens is thinking about environmental issues. So I showed this picture on the left where we have the sediment being mobilized. There's two questions here. One is, what are the environmental effects of that? So if we have the sediment moving around, is it exposing chemicals or contaminants that might be in the seabed that were buried and not affecting anything, but now it's into the ocean? It's also changing the turbidity of the water, so the water is not as clear, and this has effects on sea life. But on the flip side, the protection provided by the sort of near structure environment actually can provide a beneficial impact to the local ecology, right? So if we throw a bunch of rock on the seabed, that's going to destroy what's on the seabed to begin with, but maybe that forms a place where fish can hide, right? It forms like a reef, so it has this sort of reef effects impacts. And one thing that we're trying to look at the moment is thinking about the type of material that we use for the scour protection. Can we do that in a way that is more attractive to the sea life? So instead of, you know, just rock or pieces of concrete, we make the concrete out of a certain material, we make a certain shape of it, and then we can then use that to become more attractive to corals, more attractive to fish. And so we have potentially a net positive benefit on the local ecology. Right, last sort of, I don't remember when I started, so I don't know how much time I have left, but last sort of thing, just to point out, this is not too much on specifics, but just kind of point out the consequences of things that need to be considered when we're talking about offshore wind, is the cables. So normally the cables with wind turbines that are in relatively shallow water, say less than 50 meters water depth, we have the cables, which are high voltage cables that transfer that electricity back to shore and then connect back to the grid. These are typically buried. So they're buried to protect against anchors from ships or trawling nets from fishermen. And so they have to bury them in the sand in order to keep them from being snagged and pulled out of place and that sort of thing. So there's a couple of issues in terms of that. So one thing is in terms of the design depth of the trench. So we have these trenchers, which are commonly used in offshore oil and gas, trying to use them again for cables to trench them underneath the seabed to protect them. But the question is how much soil goes back on top of the cable. So if there's not enough soil on top of the cable, then they're not actually protected potentially. So there's a lot of research going in to see how does the sediment redeposit on top of the buried cable and what is the actual depth of that embedment. The second thing, which is an issue in a lot of places in the world, depends on where you are, is thinking about sediment mobility and bed forms. So for instance, here we've got some pictures, I believe this is from the North Sea, where we have what's called sand waves. These are basically hills, right, which are in the ocean. They can be up to 10 meters in height in some places in the world. And these things can move, right? So imagine you have a hill outside your house, it's 10 meters tall, it's there one day, you come back the next year, it's moved 10 meters towards your house. That's probably not a good thing for your house. It's also not a good thing for the cables. One main issue with that is if we do have the amount of cover that we expect over the cable, those cables are hot. So as we talked about thermal energy, also the cables which are transmitting the high voltage power are also very hot. And so they need a certain amount of heat loss to prevent them from basically cooking themselves, right? And so otherwise they'll overheat. If there's too much insulation, they'll overheat and all the cables in here will burn out. And so they're designed for a certain amount of thermal heat loss. But the problem is, what if we have this 10-meter sand wave, or 10 meters, 2 meters, even 2-meter sand wave come along and add more embedment? So there's more soil cover above the buried cable. That's going to reduce the amount of heat loss that can be transferred from that cable out into the soil and then into the ocean. And that is going to reduce the efficiency of that heat transfer and therefore lead to potentially overcooking, or not overheating of the cables, and therefore cable faults and that sort of stuff. And this is a big issue. They recognize it in Europe, but it's something to sort of keep in mind about how the seabed, which might be dynamic and mobile, will interact with the infrastructure that we put on it. So those are mainly just a couple of takeaways. Also got a nice picture here of some sea life around. This turns out to be a gas pipeline, but any infrastructure we put in the ocean, we can think of it as a way to hopefully positively interact with that environment. But we do need to think about scour and sediment transport that can occur when water will move around this infrastructure. And kind of the takeaway, just to remember, if you're ever involved with this sort of stuff, scour is important. It can be a big design driver. So just remember to keep that in mind. And that is the end of my talk today. Thank you very much.
Thank you, Joe. Great presentation. I'm sure that there will be many questions. We just run out of time. So we have to move for the next one, but I am sure they will
Thank you.
follow up here. Okay, our next speaker is Professor Camilo Arancibia from the Institute of Renewable Energy, and he will discuss now on another topic, which is solar energy. Professor Arancibia.
Thank you very much. I'm very glad to be here in this meeting between the University of Illinois and UNAM. So I will outline just some of the activities we are carrying out at our institute related to concentrated solar energy. And in particular, at this occasion, I want to talk about solar thermal processing of biomass. Many of the activities of this described here have been developed under the Mexican Center for Innovation in Solar Energy, which is an initiative from the government. For the last 10 years. We have had a large project involving many institutions, very similar to that described for the Mexican Center for Innovation in Ocean Energy by Dr. Rodolfo Silva a few minutes ago. So we are the group that we carry out research in processes with concentrated solar energy. And we are 4 academics in the institutes. We have several internal collaborators. We have also external collaborators and many students, but it would be too much to have all the names here. So I just want to emphasize that we work in a network which allows to have the input from people from many different fields of research, which is very useful for us. So why concentrated solar energy? Because Mexico is one of the countries which has the best solar resource in terms of direct solar radiation. This is the solar radiation that can be concentrated by using mirrors mainly. And so we can use this kind of concentrated solar power to generate high temperatures, so we can drive processes at higher temperatures that normally allowed by solar energy, and therefore more efficient processes. And that's why this is a strategic area of research in our country. In particular, biomass, we can process biomass by using solar energy. Thermochemical processes for conversion of biomass are generally 4. Combustion, which is the more traditional use, pyrolysis, gasification, hydrothermal processing. In all these processes, we can put solar energy into the biomass. In combustion, of course, we can burn biomass by using a concentrated mirror, but then the amount of solar energy we put in is very little. In the other processes, we can actually obtain products which incorporate a large amount of solar energy in the form of solar fuels. Pyrolysis and gasification work with dry biomass, and hydrothermal processing works with wet biomass. Pyrolysis is a process where you heat biomass in the absence of oxygen, so there's no combustion, but there's a conversion of biomass in different products. In gasification, you use either CO2 or steam to obtain different gases, synthesis gas from the gasification of any carbonaceous material, even fossil fuels. And in hydrothermal processing, you have to process in water at high pressures. So the first processes require drying of the biomass, but this other process, even though it doesn't require this drying step, it requires high pressures. Our tool for working with this kind of processes is the high flux solar furnace of the institute. This is located at our facility in Temisco, Morelos, very near to the city of Cuernavaca, 60 kilometers away from Mexico City. And this solar furnace was developed in the National Laboratory of Solar Concentrating Systems and Solar Chemistry, led by Dr. Claudio Estrada. It started operation around 12 years ago, more or less. And is a solar furnace is essentially a static solar concentrator. And in the focal region of this concentrator, we can put different experiments to use concentrated solar energy to carry out different kind of processes, to direct solar radiation through to this fixed concentrator. We use a sun tracking heliostat, which in this case is essentially a very flat mirror. And we have a shooter. This shooter we can open or close to regulate the amount of solar radiation we let into our process, and then it can be used to regulate the temperature of the processes. This solar furnace is one of around 10 facilities of this kind in the world. This is a very high concentration one with a peak of 18,000 times concentration of solar radiation. And we've been able to reach in the initial tests of this furnace, we were able to reach the melting point of tungsten, so a very high temperature. Of course, most of the processes we are interested in are do not require this level of temperature. Here we have a glass reactor where we carry out the pyrolysis experiments, and here we have a crucible, a ceramic crucible, and the biomass. Here the biomass is radiating thermal power after shooting the concentrate. Hot biomass will radiate solar energy. So typically in the experiments, we have a heating ramp, and then when we reach the desired processing temperature, we have some residence time. And we have been able to process different kinds of biomass. Just as an example, we processed pecan nutshell residues, which are produced in large amount in the north of Mexico, mainly Chihuahua and other places. And with this pecan nutshell, we were able to obtain porous carbon, porous activated carbon, and this carbon was tested by a colleague for use in supercapacitors. Supercapacitors are devices used to store much higher densities of energy than normal capacitors, but with a faster discharge time than batteries. So it's a kind of intermediate device. And here we have the result of testing of many cycles of these different supercapacitor prototypes. And in particular, we have a comparison, for instance, here with a conventional material for the electrodes, showing very interesting results for the solar produced carbons. Let us remark that generally in the pyrolysis or any thermochemical processing of biomass, the energy supply has to be by means of either fossil fuels or part of the products of the process. So reducing the efficiency and reducing the environmental soundness of the process. The other process we have been working in recent years is the hydrothermal liquefaction. The hydrothermal processing of biomass is maybe described with this, which is the based on the saturation curve of water. So when you work above the saturation curve, you have a high pressure, then you continue with liquid water at high temperatures. And in these conditions, the reactivity of water is highly increased. So we can obtain either solid, liquid, or gaseous products, generally a combination of them, depending on the temperature and pressure of the conditions of work. In this case, thank you. In this case, we worked with agave residues from the production of mezcal, and we use essentially a pressure vessel with inlets for temperature and pressure measurements. And we had studied so far the composition of the products depending on the temperature and pressure and initial pressure of operation. Here we have samples of the product and after extraction of the oil. We have not been able, due to the pandemics, to make so many analytical tests to see the composition of these products, but that is an ongoing work. Finally, let me just mention that an important part of our work is the optimization of solar reactors to achieve, for instance, in this case, much more uniform distribution of temperature between the different components of the reactor. Thank you very much.
Thank you, Professor Arancibia. We run out of time, so if you have a question, please leave it on the chat, and hopefully Professor Arancibia will answer those. So our next speaker is Professor Octavio Garcia from the Institute of Renewable Energy, and he will follow up with solar energy on solar drying.
Okay, thank you very much. I'm Octavio Garcia. I'm the leader of the solar drying group in the Institute of Renewable Energy. And the introduction, the loss and waste of food that occurs in the production, storage, processing, and distribution stacks has a negative impact on the environment through the use of water, land, energy, and other natural resources to produce food that no one will consume, and additional produce CO2 emissions. In Mexico, it is common to observe open sun drying. However, the products are susceptible to attack by fungi, insects, birds, rodents, unexpected rains, and other meteorological effects. Approximately 37% of food in Mexico is lost. Wasted food will be enough to avoid the hunger suffered by 7 million people in Mexico. Given this scenario, we consider essential and strategic the creation of community centers for solar drying of agricultural products from small producers in rural areas in order to strengthen the development of agricultural sector as well as to reduce hunger and poverty. It is also necessary to reduce energy consumption in the food sector and to decouple prices from unstable and increasing prices of fossil fuels. Therefore, it is desired to use renewable energies to dry agricultural products. For this reason, the solar drying group has developed different types of dryers, from domestic to industrial use, to dry agricultural products with 100% national solar drying technologies. This is our small dryer with a capacity between 0.5 and 2 kilograms of fresh food to promote the use of this technology or to be used in waste food at home. This is a bigger one, capacity between 10 and 20 kilograms of fresh food to be used by small farmers from marginal rural areas or self-consumption. Small drying tunnels, capacity is between 20 and 50 kilograms of fresh fruits to be used by small farmers. We also develop greenhouse dryers, capacity between 100 and 1 ton of fresh food. And we have 2 experimental plants. This is a hybrid thermo-solar plant for the hydration of food products. Was designed, installed, and tested in Xochitepec, Morelos. The plant is integrated by the drying chamber with a drying area of 56.3 square meters. The requirements: energy is provided by 2 solar thermal systems, an air heating system, and a solar water heating system, both with 16 solar collectors, 40 square meters, a thermal storage tank, 2,500 liters, and an air water heat exchanger. The plant has a fossil energy backup system of LPG to heat air with hot water and the air water heat exchanger. The monitoring system measures and records different process variables: temperature, relative humidity, solar irradiance, air velocity, water mass flow rate, and has a capacity up to 500 kilograms of fresh food. This is the photography and the diagram of this plant, and this is the monitoring, the measurement sensor that we are installing in this plant in Xochitepec, Morelos. And this is only photographs of the drying pineapple in these facilities that we have. Another important plant, a bigger one, is the solar LPG gas hybrid drying plant designed, built, and tested in Zacatecas. The drying system is a forced convection hot air type with a drying chamber. For the air heating requirements in the drying process, there are 2 solar thermal systems, a direct air heating system, 48 solar air heaters developed by us with an area of 111 square meters, and an indirect air heating system, 400 solar water collectors with an area of 92 square meters and 9,000 liters of thermal storage tank, with a backup system of LPG burning. This capacity of this plant is up to 2 tons of fresh food. This is the diagram of this plant. This is also the photography of this plant with the flat plate solar water heaters that we use and the solar air heaters that we develop. And we also, in these plants, we make drying synthetics. For example, this is a drying synthetic of nopal when we use the solar air heaters, the water heaters, and also the LPG burning in order to dry this nopal. And this is also a photography of our plant in Zacatecas and the drying nopal, and we can convert the nopal in flavor for different things. And our group has some projects approved or under development. Some of them are, of course, of solar drying, and we are working also with small indigenous producers in Hueyapan and also with small or big producers in Zacatecas. These are our projects approved and under development. And this is also some representative scientific productions of our system that is about the development of, for example, solar air heaters, or the tests in some solar dryers, or our plants that I show you. We have some articles about this line of solar drying technologies. And also we have some patents. We have patents about the solar air heater. We have patents about the solar drying processes and infrastructure that we have developed. And this is the list of our collaborators and our internal collaborators in the Institute, and also external collaboration. It is very important for the communities to work with specialists on community works, in this case, Magali and Rocio, and we have also collaboration with with other Mexican universities, and also with other countries of Iberoamerica that are working in similar aspects of these kind of technologies that are used in order to dry food products. Thank you very much. I'm Octavio Garcia Valladares.
Thank you very much. Thank you very much for the presentation. We have a few minutes for questions.
Well, I was wondering if you work with cereals and legumes like beans or corn or just fruits and vegetables.
No, we are working with all of the agricultural products. We work with beans, we work with cereals, we work with legumes, and we are working with different kind of products, and we make the drying synthetics, and we try to use our technology in the best way for this kind of products.
Mm-hmm.
And also we evaluate the final products, the vitamins and proteins and the things that we obtain of these drying products.
Wonderful. Here at Illinois, we have what is called the Post-Harvest Technology Institute, and it's very engaged with different countries in the drying and preservation of many commodities, such as cereals and legumes. So it would be nice to talk to you later. Thank you.
Of course. Thank you very much.
Thank you.
Any other question?
I have a brief question, Octavio. Thank you for your presentation. I'm wondering about in the operation of this solar natural gas system, how do you deal with the intermittency of the solar power? Is that primarily compensated by the natural gas, or do you have other kinds of storage mechanisms in place?
Yes, we have of course the LPG burner in order to compensate the energy, but we have a storage tank of 6,000 liters in the case of Zacatecas. We begin to dry with solar air heaters, then we use the solar water heaters during the solar day, and after that we have another 3 or 4 hours with our hot water that we produce in the solar water heating system. Then we can operate this plant about 12 hours with solar technologies, and the rest of the day, of course, or at night, we can use the LPG facilities.
Okay, thanks.
Perfect. Thank you very much again. Okay, let's move to our next speaker. Professor Wilfrido Gomez from the Institute of Renewable Energy at UNAM, and he will continue discussing related topics with the solar and refrigeration and heat pumps.
Good morning, everybody. And thank you very much for the presentation, and also thank you for the invitation to participate in this symposium with the University of Illinois. I'm not sure if you can see my presentation, can you?
Yes.
Okay, thank you very much. Well, I'm going to start. The title of the presentation is the Solar Refrigeration and Heat Pumps Group. This is a small group. We are just 4 academics working right now. We used to be 6, but 2 of them have retired. And of course, we have postdoctoral students as well as postgraduate students working with us. Okay, the contents of the presentation. First is going to be the introduction. Then I'm going to talk about the solar absorption cooling cycles. Then about the thermodynamic cycles for the power and cooling production, and some of the achievements that we have get from the work done. So about the introduction, it's important to say that the energy consumption for space cooling has more than tripled since 1990. See, this is according to the International Energy Agency. And the second is that the space cooling accounted for nearly 16 of building sector final electricity consumption in 2020. It is expected that the usage of these conditioner systems will rise from 1 billion to 5.5 billion in 2050, and the domestic refrigeration will double and will reach more than 2 billion. Absorption systems may play an important role in reducing this consumption of conventional fossil fuels since they can be driven by renewable energies or industrial waste heat. And it's exactly in this, with this topic that our goal is exactly to develop absorption systems that could be driven using thermal energy. This thermal energy could be provided by solar energy, but of course as geothermal, and also industrial waste heat. The potential of industrial waste heat is huge around the world. So first, I would like to introduce what are absorption systems, and in order to do that, I would like to show you what is a conventional system. Okay, a conventional system, which is the system that we have for air conditioning or for refrigeration, consists of 4 elements, which is a compressor, a condenser, an expansion valve, and evaporator. See, and of course a refrigerant circulating through the cycle. See, power has to be supplied to the compressor in order to upgrade the pressure and temperature of the condenser, the refrigerant. So the refrigerant at these conditions is condensed in this component and then is expanded, reducing its pressure and its temperature. So the temperature obtained after the expansion valve is lower than the food or the space that we would like to cool. So in this way, we create the cooling effect here in the evaporator. And the refrigerant is then compressed again by the supplying power. Well, the absorption cooling systems, as you can see, the left side has the same components, which is a condenser, expansion valve, and evaporator, exactly as the mechanical compressor system. But instead of having a compressor, we replace the mechanical compressor with something that we call a thermal compressor. In this thermal compressor is composed of a generator, an absorber, a solution heat exchanger, which is not mandatory to be there, but is useful in order to recover the energy to make it more efficient, a valve and a pump. Okay, and the idea of these systems is that instead of just a refrigerant, this system operates with a refrigerant and with an absorbent. So if we have this mixture here in the generator and we heat it up, then we can produce the refrigerant, and the refrigerant will follow the same path as the mechanical compressor cooling systems does. So it condenses, expands, produces the cooling effect, but then it's going to be absorbed by the solution poured in refrigerants, leaving from the generator, going to the absorber. So in this component, the solution is formed again with a high amount of refrigerant, and then is pumped to the generator, starting the cycle. Okay, you probably say, okay, but instead of having just one component, we are replacing for a generator, an absorber, a valve, a pump, etc. No? Okay, but the advantage of this system is that the main energy supplied to that is thermal energy instead of power. Okay, but even though we can do this system even simpler, and as you can see here, if we trace a diagonal line, we can find the condenser, the expansion valve, and the evaporator exactly in the same way that the other systems. But instead of the mechanical compressor, we're putting here the generator and the absorber. Okay, this is just one component, but operating in different moments. If we put the solution into the vessel, let's say, and we heat it up, then we can produce the refrigerant, we condense it, and we storage during the day time. At night, the pressure of this component goes reduced, and then we can open this valve, reducing its pressure, and then we can produce the cooling effect, and then it's going to be absorbed to be ready to operate at the next day. So this is and this system, the important is that it doesn't use any electricity at all, okay? Well, with this idea, we started to develop a cycle. See, we're here in the focus line of this collector, we have the vessel, see, where we storage the solution. So this is the generator. We have the condenser, the storage tank, and we have the evaporator to produce the ice. So we develop the prototype, and here's the prototype. And we can produce ice, as you can see, without using electricity, as I mentioned, and different ways. It could be in plague, or it could be in cylinders, thin ones or larger ones. No? But coming back to the absorption systems, okay, we said that this is the cycle, and we have developed some prototypes based on this cycle, and all have been made in Mexico. The idea is to develop Mexican technology. And you can see from a schematic diagram, how can we pass to build the components, and then just to build up pilot plants, no? Or we have developed the systems, and some of them have been, some of them are operating in different parts of Mexico. See, with solar collectors, you can see here, this is an example that we have developed. And in order to compare our technology with other one, we have run our systems in parallel with other systems that we can find you commercially available. So, and what we found is our prototype. It's about the same capacity, even a little more than the commercial systems, with a maximum coefficient of performance, which is the efficiency in this kind of systems. And while the other commercial systems is only could be used for air conditioning, our system can be used for air conditioning and also for refrigeration. And if you see, the size of the system is similar to the commercial one, but the big difference is that this costs 1/3 than the commercial one. Okay, but we have developed even smaller systems, as you can see here. This is another system. This is the last that we have developed. And some of the pieces that you can see here, they are Coriolis flow meters. And if you remove them, because in a commercial system, you need to use them. So the equipment is very compact. So we have developed that right now. And moving to another research line that we have working is in thermodynamic cycles for the simultaneous production of power and cooling. So in order to do that, we follow one work published by Dr. Yogi Goswami, which use a similar system, see, with the generator, economizer, and absorber, etc., the cooler. But instead of putting an expansion valve, he proposed to use a turbine in order to produce power and cooling. Okay, well, this system exists, has been built, and it's been successful when it has been installed. But the problem is that the cooling effect is much lower compared with the power produced by the turbine. So taking at this, we have developed our own cycles, thermodynamic cycles. And as you can see, we have added a condenser and also an expansion valve, just making an extraction from the turbine. And with this idea, now we can use not just a cooler, but also an evaporator and a condenser. And with this modification, the system is capable of producing considerably more cooling than the other cycle percentage. So for instance, this plot shows this is the energy utilization factor, which is about the efficiency of the system, which it combines the power and the cooling produced to the power supplied. So the reference cycle, the energy utilization factor should be around here because the cooling production is very slow. And with this modification, the energy, the total energy that we are producing is considerably larger. So this is an advantage over the other system. And this is another system that we are working for, which are organic Rankine cycles integrated to cooling systems. This is a cooling system, but this is a double effect system in order to make it even more efficient. So with this kind of cycles, we can produce more power and also more cooling. So that's the idea. Of course, they are more complex. And
un minuto, Profesor Rivera Gómez, un minuto para cerrar to close the presentation, please. Thanks.
Thank you very much. And with this kind of systems, you can achieve higher efficiencies. So if we have a cooling systems, we integrated a micro turbine to it, so we could be able to produce power and cooling simultaneously. So this is the things that we are doing in our group. And some of the achievements that we have gotten are the following. We have published more than 150 international papers with more than 5,000 independent sites. We have developed several prototypes. We have 8 patents, and we have requested 4 more. We have graduated more than 50 students. We have been awarded with different national awards for the development of cooling prototypes, thesis directions, and some of us, we are belonging part of the International Energy Agency in the solar cooling, heating, and heat pump programs. So thank you very much for your attention. My name is Wilfredo Rivera, and that's my email. If you want to make some contact, I will be grateful to.
Professor Rivera, thank you for a wonderful presentation. If anybody would like to ask a question quickly before we move to the next presentation, please.
I want to congratulate the professor for extraordinary presentation and wonderful accomplishments. It's an honor to have you here, Dr. Rivera. Thank you.
Well, thank you very much for your invitation. Thank you very much to all of you.
Thank you. Our next presenter, Professor Sebastiano Giardinella. Dr. Sebastiano Giardinella, who will talk about energy storage at a natural gas pipeline.
Thank you. First of all, can you see me look at my presentation?
Yes.
Okay. Thank you. Well, good morning. My name is Sebastiano Giardinella. I'm a project engineer at the Illinois Sustainable Technology Center, University of Illinois at Urbana-Champaign. ISTC partners with companies and other institutions to perform basic and applied research on carbon capture, energy and sustainable technologies, and several technology demonstration projects at the university and large industrial sites. We have been awarded over $100 million with our main funding from the U.S. Department of Energy. On behalf of the project partners shown below, I will be presenting a DOE-funded project to develop a concept for a compressed gas energy storage system integrated with our Abbott combined heat power plant. First, a disclaimer, as this project was funded by the U.S. government, but it does not endorse any particular technology shown. With this, the challenge that we're addressing with this research is to develop systems and methods that enable intermediate renewable energy sources to increase their share of grid electricity, while also responding to demand curves, helping to solve planning difficulties for system operators, and maintaining low system costs. And ideally, the proposed solutions should not be constrained by geography. With these challenges in mind, we have proposed compressed natural gas energy storage, or CNGS. CNGS operates through compression and expansion of a working gas. In off-peak periods, excess renewable energy is used to compress gas, which is stored in a vessel, underground, or in our case, at a pipeline. During peak periods, part of the energy used in compression is transformed back to electricity using an expander generator, which is a mature technology. Now, you here may have the question, why using a natural gas as a working fluid? So, a rationale behind using natural gas is that, one, it is already used as an energy carrier and widely deployed in power generation. Two, it is abundant in the US, also in Mexico, with a very well-developed network for compression and storage. 3, it has a value that covers the cost of compression and storage already embedded into the price of the gas. Taking this into consideration, some preliminary estimates that we did before this product indicated that this technology could be able to compete with compressed air energy storage and pumped hydro storage in the high power output, long duration energy market. Now we had to test the original assumptions in a real setting, which brings us to our present project. The goal of the compressed natural gas energy storage at Abbott Power Plant project was to perform a phase 1 conceptual study to integrate CNGS with the existing 85 megawatts combined heat and power plant at UIUC in Champaign, Illinois. This phase 1 study included performing a conceptual design, a techno-economic assessment, identifying technology gaps for commercialization, market potential, and steps needed to mature technology. The CNGS concept was separated into 2 stages, in a manner that reflects the way we expect the technology would be able to deploy commercially. A first stage of the deployment would seek to utilize the existing facilities for storage. That is, existing compressors would transform electricity to potential energy, and existing pipeline will provide a volume to store the gas within the constraints of its maximum and minimum pressure limits. At the end of the pipeline, new expanders will be installed at existing pressure reduction stations to recover part of the energy using compression and convert it back to electricity. We expect this arrangement to facilitate deployment as relatively small additions would tie into existing infrastructure. A second stage of deployment would see us increasing the storage capacity by developing new infrastructure that would complement the capacity of the stage 1 facility. This would include new compressors to increase the pressure of the gas beyond the limits of the existing pipeline, and then storing the gas in additional high pressure containers. The model approach we developed allowed increasing the capacity of the system to 12 hours for the study, but it could potentially be larger as limited by space. This stage would give more flexibility and resiliency to the fossil asset in the case of large fuel price variations or disruptions in the gas supply, but would be more costly and take longer to develop. This satellite image shows how the systems are geographically located. Stage 1 involves adding new expanders to 2 pressure action stations located on site B and C, separated by pipeline, which are going from A to B to C. These lines shown here represent the whole pipeline separated into 2 segments, totaling 22 miles, and this is the volume that we're using for storage. So on stage 1, we'll be adding expanders on sites B and C, and stage 2, we'll be adding also compression on site B. This render that was developed by the engineering firm as part of the partners in the project shows how the net facilities would tie in to the existing ones at sites B and C. So these new facilities are the ones highlighted in blue, with the blue equipment being the expanders and the heaters, and the green lines being the pipeline with the tie-ins. After doing the engineering study, we evaluated the impact on our system, and the impact of energy storage on the university grid can be seen here. To the left, you can see the current load and generation profile of the university grid. The yellow line represents demand. The red area represents thermal energy, and the green area represents solar PV electricity. These are our averages. The gray area represents energy that is being purchased from the grid to balance the rest of the demand. On the right, you can see how the blue area, which represents the energy delivered by the energy storage system, replaces grid electricity. The charging and discharging cycles are set in order to reduce the amount of peak consumption from the grid. In total, both stages have to 387 megawatt hours of potential plus chemical energy, storing energy for 12 hours based on the combined power plant natural gas turbines consumption. By replacing grid electricity imports, the system avoids emissions as shown on this table. This is due to the emission factor of the system being considerably lower than the average emission factors for linear grid, which are represented by blue columns. So the expanders, they do not burn gas, and they recover the energy from the pressure drop, but as still a small amount of gas is being burned, so it would heat up so that the temperature after the expanders do not fall below freezing. And this is mostly on winter. Now we come to levelized cost of electricity. We have other different cases for this cost. In the upper chart, you can see how for the Abbott power plant's demonstration projects, we estimate a cost of $51 per megawatt hour. This is including capital and operating expenses on its life cycle when integrating with the power plant. So we then use scale-up factors to estimate the projects, the cost of a project at least 10 times the size of our demonstration plant. And for this one, we are able to lower it to $49 per megawatt hour for the energy storage integrated with the existing power plant. These values are then compared against the orange columns, which are the estimated cost of a new installation with battery storage as predicted by the annual energy outlook in 2021. Based on the results, we foresee economic and operational benefits of applying technology over different industries. So in conclusion, we completed a 307 megawatt hour self-power storage project in 2 stages. The concept is scalable and the economics favor larger projects. As another collaboration, we are open to teaming up with any potential researchers and companies that wish to implement new technologies at our university and our center. And we have facilities here that can use.
1 minute, please, to finish. Thank you.
Okay, thank you. We have the ability here to test new technologies. We have a grid owned by the university and operated by it, and we have different sources of electricity. We'd like to thank the DOE for funding these projects. And these are references. On ideals, you can see here a full version of the study. And then there's another article that was published in Power Magazine where you can see the summary. With this, I'm open to questions, and thank you.
Thank you very much for the presentation. Are there any questions that can be directed to Dr. Jardinella at this point? Okay, one more time, thank you very much for the presentation. And we are going to go on to our next presenter, Professor Joaquin Rodriguez from the Department of Chemistry at the University of Illinois, who will talk to us about the title, as you can see on the screen, Gearing Up Electrochemical Microscopy for Observing and Controlling Interfacial Processes in Energy Storage and Conversion. Professor Rodriguez Lopez, please. Thank you.
All right, thank you very much. Well, first of all, thanks for the opportunity to be here. And I guess this is where we switch a little bit gears, because we're gonna be talking about more microscopic thing rather than big storage tanks and things of the sort. But I'm a professor in the Department of Chemistry, so that's what we do. We do chemistry. And particularly, my group is really interested in energy storage interfaces. So the idea that we make batteries, we make electrochemical devices, and all of these are driven very importantly, not uniquely, but importantly, by things that happen at this electrochemical interface. In the particular case of batteries, we know that these interfaces can be controlling. Without the solid electrolyte interface that forms on the surface of your battery, it wouldn't work. It would explode immediately. And so understanding how this its reactivity is develops, how it can be heterogeneous, how when you change the rate at which you charge and discharge the battery, the properties of this interface can actually make a difference in how it behaves and how things behave as they evolve, right? So doing the first cycle on a battery is not the same thing as doing the 1000th cycle on a battery. And so trying to understand those processes is really important, especially when we start to depart from lithium ion. So what happens when we start thinking about other technologies such as potassium ion batteries, or when we start thinking about sodium ion batteries, for which little changes in the chemistry can actually mean quite a bit. And so my group, for this purpose, has developed an integrated set of tools to understand these processes. In my group, we do electrochemistry, very fundamental electroanalysis. And so we use a technique that is called the scanning electrochemical microscopy. The idea that you can use a really, really tiny electrode that you can put very close to an interface and learn about what that interface is doing. We have projects that deal with oxygen evolution catalysts. We have projects that deal with photoelectrochemical processes. We have projects that deal with the production of hydroxyl radicals for the remediation of wastewaters. And just as we do try to understand all of those chemistries, we also try to understand the chemistry of batteries. So in this particular case, I'm going to tell you a little bit about a probe that can detect lithium ions, and then I'm going to tell you, a little bit more briefly about some of those other directions. So for instance, all the experiments that we do with this microscopy technique are done in a dry box. We developed this little probe that consists of a really, really tiny droplet of mercury that is capable of reducing lithium ions and to be sensitive so that we can make a little sensor that can actually tell us about the concentration of lithium ions, and that then we can use to put in the vicinity of an active electrode that is doing all of these chemistries, right? That is intercalating lithium ions, but also generating decomposition materials on the surface of this electrode. And so in this study, we developed this technology in which we can find the active area of a carbon material that intercalates ions. And then with our little probe, we can see when the ions come into the material and when the ions come out of the material. So we can track those intercalation processes. What that was really important is that in this particular application, we were able to see the region where lithium ions come in and when they come out. And this is the part that is important for your battery, the part that is storing ions. But we also discovered that this layer of decomposition products that forms on the surface of your electrode is actually intaking and then releasing a very large portion of these ions, which was actually quite a big surprise. It turns out that also our technique can be used to directly probe the kinetics of ion intercalation, which is something new. This type of studies can only be done using very complex techniques based on impedance models. But in here, because you can actually see how the ions come in and out, you can actually get a first look at those kinetics. So that was one example. We couple also this microscopy with new concepts of materials. And so one other thing that we have attempted to do here is to think, hey, if you really want to look at these very, very thin interfaces that form on the surface of electrodes, why don't you make an electrode that is already atomically thin, right? That it's just as thin as a few atoms, so that whatever happens on that electrode, whatever interfaces you form, are really, really going to control the behavior of this electrode. And so one example of this was a study in which we tried to intercalate potassium onto multi-layer graphene. Turns out that multi-layer graphene, if you put it in a lithium electrolyte, not a problem. Ions go in, ions come out. Very nice response. But if you put it in a potassium electrolyte, instead of forming an ions come in, ions come out scenario, what you end up doing is that you end up plating potassium over that interface. And that's not what you want to do, okay? And so it turns out that the trick to do this right was to first intercalate lithium ions so that you form that layer, and then you intercalate the potassium ions with that layer, okay? And then you get a beautiful response. So you see almost no difference in the shape between the intercalation of lithium and potassium, but potassium intercalates at a much more negative potential, so it gives you a little bit more energy density. And we were even able to make sure that it's potassium, because it turns out that you can intercalate just slightly less potassium than you can intercalate lithium, and that's why this curve is slightly smaller. You can do this very fast because these are very thin electrodes, so it really gives you access to doing very high velocity, high-speed experiments. And then you can do a bunch of other really cool things. So for instance, we took our electrodes to the materials research lab in here, where we have a time of flight secondary ion mass spectrometer, and we can actually say, hey, look, as you start to run this lithium SEI on a potassium electrolyte, you're actually incorporating more and more and more and more potassium on this SEI. And we can see that because we're sputtering material out of that SEI, in all of these different electrodes. And of course, we can characterize and see the differences between all of these electrodes. So really interesting point. Finally, our SCCM, so I showed you how we have used it before to detect lithium ions coming in and out, but our SCCM can also be used to probe the passivation of this interface as the SEI forms. Turns out that the SEI, this layer that you form, it's electrically insulating. It's ionically conductive because lithium ions have to go in and out, but it isolates you from electrochemical processes. And so by using a redox mediator that we, kick back and forth between the tip and the substrate, we can actually see how at the beginning we have an active electrode, but then as we start to form more and more and more of this interface, you end up actually with a completely passivated surface. It turns out that this phenomenon is really, really interesting because if you apply it on with much smaller electrodes, and here we're using a 300 nanometer electrode, and you actually start looking at this type of videos, right, where as you cycle the electrode, you're capturing one image and you can see the passivation in more or less real time as it is happening. So you can measure it as well, the rates of these processes, and of course, then you can make comparisons. And one of the really interesting things that we found is that, this process happens very readily and very completely on lithium. But if you try to go to other types of batteries like potassium or sodium, they don't passivate as well, not initially. And so this is actually one of the reasons where perhaps this type of SEIs that form on these other electrodes are not as well performing. The final application that I'm going to show you is that we can also couple this SCCM concept to other things like doing a spectroscopy. So in my lab, we have been doing this coupling of SCCM with Raman spectroscopy. And the idea is that we can use the SCCM to get maps of the reactivity of an electrode. In this case, it's a carbon electrode that has different layers of graphene, 8 layers outside, 3 layers inside. And you can see that our little scanning electrochemical probe can say, okay, the rate of electron transfer is higher outside, is lower inside. And at the same time, the Raman imaging can tell us, oh yeah, this is because in the inside you have a lower number of layers, fewer layers, and on the outside you have a higher number of layers.
One more minute, Professor Rodriguez Lopez.
We can do in situ experiments to show also how, at the same time when we're doing something to that interface, the rates of electron transfer change. And so that's also a pretty exciting prospect. And recently, we also demonstrated that we can do this Raman SCCM also using surface-enhanced Raman spectroscopy. So in principle, we're increasing very dramatically the sensitivity of this technique. And so with that, that's basically what I wanted to share with you. As I mentioned, all of these techniques are things that we use for batteries, but we also use for electrocatalysts. We also use for water remediation systems. We use them for many purposes. So we would be really happy to discuss with you about other prospects. And with that, of course, acknowledging my group, our funders, and to say thank you and give you our contact information in case you're interested in reaching out.
Thank you very much for a fascinating presentation, Professor Rodriguez Lopez. Anybody who has a question before we move on to our next presentation?
I just want to congratulate Professor Rodriguez Lopez for a fantastic, wonderful presentation. Thank you for your constant support to I-MMAS.
Thank you, Elvira. Not a problem. Very happy to be here.
Great. All right, our next presentation is by Dr. Marina Rincón González. She comes to us from the Instituto de Energías Renovables de UNAM. And her presentation is Electrochemical Energy Storage, Materials Design and Interfacial Characterization.
Hi. So I'm Marina Rincón. I'm the director of the Renewable Energy Institute. I'm happy to be in this initiative from the University of Illinois and our university at UNAM. I'm so happy that Joaquin was first than I, so I'm very, very lucky. But let me tell you that I'm really fascinated with all these talks, particularly because I'm a material science. So all this engineering stuff was very, very useful to me. I'm very, very happy to be here. Well, I'm gonna talk about electrochemical energy storage. So let me share my my presentation. Here it is. So, you see the presentation?
Yes, it looks good.
Okay, so now it's in the presentation mode. First, let me introduce to the team. Is Oscar Jaramillo Quintero. He's a young researcher working on lithium-ion battery and sodium-ion battery. Margarita Miranda, that has a very strong electrochemical background, so Joaquin knows her very well. Hugo Olvera, that he is on the for electrochemical and electrochemical conversion, so his work is more related to the chemical storage. So in this small presentation, in this small compilation, I will just talk about the work on batteries. Particularly this alkaline metal battery. And I'm going to put everything in context. So if we are really in the, I'm going to turn off my camera. So, can you see, can you hear this okay? It's okay for you to?
It looks just fine. And you can continue to have video because the presentation is on the whole screen.
Okay. So to put everything in context, so to talk about this carbon neutrality goal that everybody is pursuing, that means to avoid 51 billion of CO2 equivalent into the atmosphere. But Mexico only contributes with 1.3% of this amount. And this is easy to see because look at those numbers, 3.7 ton emission per capita in Mexico, versus the 16.5 ton per capita in the United States. That says a lot about our way of living. So anyway, in Mexico, it is true, most of our energy portfolio is very focused in fossil fuels. You see here, 71, and there is a 4% in carbon. So 75% is from fossil fuels sources. And only very little amount, like 10%, comes from helium and solar, and around 11 comes from big hydro. And it seems to me that this distribution, which sectors are the worst emitters, is very similar in Mexico and worldwide. So the electricity sector and the transport sector are the worst emitter. So it seems kind of natural to think that most of the solutions implemented in the world can be applied to Mexico. That's one way of thinking. But we need to consider that in Mexico, there is 40 million of persons that lives in energy poverty. That means that they do not have enough energy to cover their basic needs. So it doesn't seem that wise when you look into that particular context. So, but it is okay. We need to transition into new technologies, but we have to do it carefully. So the goal that going everything to renewable energy kind of scare most of the people in this government. So let me tell you that Mexico is committed to do that transition. Mexico has signed a lot of international agreement that he's going to transition into the renewable energy production of electricity, and it's going to electrify a lot of the transport sector. However, it's not really what is happening right now. Right now, it seems that there is this obsession to keep the fossil fuel industry going. But there is a commitment. Mexico has signed a lot of international agreement, and let's see if that is phase 2, like they say it will be. Okay. There is another problem, and probably is the opportunity that the Mexican electric grid has a lot of congestion, and you can have these thick lines, and also a lot of diversity on prices. So the red lines means where the electricity is very, very expensive. So we have a lot of problems that has been analyzed in the terms of this renewable energy possibility. And also in some other energy storage technologies. And the conclusion was the battery was not such a big deal, such a bad idea. I'm concerned about Dr. Sebastian graph in which battery was kind of discarded. But according to these studies, the duo renewable energy and batteries was really a good idea and could really solve a lot of the problem that right now our electrical grid has. And also can be the possibility that this penetration of renewable energy can really accelerate. So that is an opportunity. Another opportunity is that apparently Mexico has a lot of lithium. So truly, there is only 3 sites in exploration. And these are in Baja California, San Luis Potosí, Zacatecas, and Sonora. 0 sites in exploitation. And our export are $350. No? Our import from Chile is $2.7 million. So we have this negative trade. Most of the lithium that we import is used in batteries, like 47%. And the potential reservoirs in tons equivalent are 50 million. So it seems that it could be really a good idea, and it's not that naive to think about this low carbon world if we storage and consider this electrochemical energy storage. Now, taking into consideration all what I have explained to you, what we are doing, a small group are doing at our institute is working on alkaline ion and organic flow batteries. Okay, we are just tackling problems on toxicity, cost, and sustainability issue, and we're working on anode cathode membrane electrolyte. And we have this goal of proving the concept. So we are using a lot of interfacial modeling and characterization along with theoretical simulation to provide insight of the various limiting the performance. And we have a commitment with low cost synthesis because we need to scale the materials to fabricate reproducible prototypes that allow us to be sure that in reality, we are really producing something that is reproducible and can be scaled from the lab to the real world. And this scaling of materials, particularly for our institute, is very difficult, it's very costly. So we are so happy to be working in a very milligrams scale, but when we want to face this challenge, we need to partner with somebody else to cover the cost.
Rincon, 1 minute, yes? 1 minute left.
Okay, and we want these safety issues during the safety issue that has to be with commercial batteries and using thermal management innovation. So to be sure, we are here. To be clear, we want to impact in these 2 sectors. And we are really betting in low dimensional materials that has high surface to volume ratio because it has short diffusion path and because we can handle it very low cost solution process techniques. The interfacial characterization that we are betting is surface for voltage spectroscopy, electrochemical impedance spectroscopy, photoluminescent spectroscopy, in situ techniques. And these are our programs, and this is the way we think. First, we tackle specific capacity, then we go for cycles, more on cycles, and then we switch from a less abundant alkaline ion to a more abundant alkaline ion like sodium. And we have been very happy that CONACYT and the GAPA have been very patient with us and allow us to have this systematic progress that put us in a position to really look for international partners to accelerate and escalate and fabricate and be really an impact in the real problems of Mexico and the world. And that's everything. Thank you.
Dr. Rincon, thank you so much for an interesting presentation. Does anybody have a question at this point?
Just very briefly, what type of organic materials are you thinking about? Are you thinking about aqueous organic or non-aqueous organic for your flow batteries?
They're thinking about hydroquinona, hydroquinona, y quinona.
Okay, so that's aqueous.
So those are the kind of things that Margarita is working, and we already write down your name, so don't worry, we'll knock the door.
Oh, it's okay. Yeah, tell her to reach out, because we have projects on that, and we're part of the battery hub also here in the States, and that's what we do. We do redox flow batteries. So yeah, that would be great.
Yeah, you are one of my interesting names.
Thank you, Marina.
Excellent. Thank you so much, Dr. Rincon. And we're going to move on to our next presentation by Professor Kyle Smith from the Department of Mechanical Science and Engineering here at the University of Illinois. Professor Smith's presentation is about electrochemistry for separations and storage, understanding transport and thermodynamics for efficient, resilient devices and materials. Professor Smith.
Thanks, Jose. Just want to check here. You do see my full screen?
No, we see your presenter screen.
Oh, yes. Okay, thanks, Joaquin. Let me just try to share the right thing here. Let's see here. Okay, now how's that?
That looks good.
Okay, well, thank you so much. It's a pleasure to be here. I actually was accidentally moved to the other room for the first hour, and I was just struck by not only in this session, but also in that one, how many connections there are to some of the work that we're doing, and I look forward to interacting with folks across the board in the future. So today, my talk is going to be on the use of electrochemical energy for both separations and storage applications. And before I jump into any specifics, let me unpack that a little bit. So the work that my group does is largely focused on devices that use electrochemistry in some manner, either to do separations or energy storage or conversion. Just listed a few of the applications here, in particular desalination, resource recovery, and some negative emissions, all of which involve some type of separations process whereby we're using electrical energy by way of electrochemical interactions. But we also do work with energy storage using battery-like devices. So all of these different devices that we work with not only involve conventional two-electrode type electrochemical cells, we also have flow that's present. So as a mechanical engineer, I find it particularly interesting the fluid mechanics and the transport phenomena that occur in concert with the electrochemical processes. And really a fundamental goal of ours is aimed at manipulating those processes in such a way to cause process intensification to occur, to enhance scale up and energy efficiency. And so the tool set that we bring to bear on problems of this sort include transport and thermodynamics, in which we also do modeling of device dynamics and their engineering, which ultimately translates to experiments that we also do. But we also make solid state materials using different synthetic strategies to act as hosts for different kinds of ions. And we do electrochemical characterization and various other kinds of characterization of those materials. So in the context of desalination, we use ion intercalation materials, some of which you've heard of both in Joaquin's talk and the previous speaker's talk. In particular, those that absorb cations that are relevant to salt water, including sodium. In the energy storage space, which I want to make sure that I give some justice to, considering that this is an energy symposium, a lot of our work is focused on redox flow batteries and the modeling of those systems. And in particular, some of our newer work in this regard has focused in particular on how these kind of energy storage devices might couple to the intermittency that is provided by renewable energy resources like wind power and solar power. and how can devices be designed in light of the fact that, in light of the physics by which the electrochemical reactions take place. But most of this talk, I'm actually going to focus on the desalination direction because I feel that it actually articulates the scope of the different approaches that my group uses. And in that context, there is a strong connection to energy. This Energy and Environmental Sciences paper, which I've shown a plot from here, articulates very nicely how among different types of water desalination processes that exist today, energy consumption is a big factor, including for brackish water desalination, for those cases represented on the plot here. You basically can run the device with a thermodynamic efficiency that's on the order of 5%. So you're consuming 20 times more energy than the thermodynamic minimum in order to cause the desalination process to occur. So there's opportunities to improve the efficiency of these kind of processes. In addition, there's another connection to energy in that the exploration of oil and also natural gas can sometimes have concomitant development of wastewater that is brine. And a common approach to deal with that wastewater is to re-inject the brine back into ground formations. And that's been linked to increased incidence of earthquakes. And here in states like Kansas, for instance, limits on the injection of such brines have actually been imposed that have led to decreased productivity of petroleum exploration. So we asked the question, what alternatives to thermal and pressure driving forces, which are the conventional means to do desalination, might we use? And so my experience actually goes back to energy storage in the postdoc that I did, and also some work in my PhD, where I understood the phenomenon that can occur inside of lithium-ion batteries when they're charged in a very fast way. The electrolyte inside of the pores of a lithium-ion battery can actually dynamically deplete within one electrode while concentrating lithium-based salt in the other electrode. And when I saw these types of phenomena occurring in lithium-ion batteries, while also having some knowledge of a need for desalination, I started thinking about, can we harness similar kinds of interactions to cause desalination to occur? Effectively, desalination is happening inside of this right-hand electrode inside of this battery. And there's been a lot of work that's been done over the past 10, 15 years to develop beyond lithium-ion batteries that use sodium intercalation, like Joaquin was describing, but in particular in the aqueous context where water-based electrolytes are used. And here I'm just showing a number of those different materials that have been developed over the past 10 years or so. And if we look at what is the charge capacity of any one of those materials in milliamp hours per gram, which is a typical battery metric of charge storage, we can convert that to some amount of moles per liter of ions stored in the solid state. So if I have a porous electrode that is 50% solid intercalation material, that actually corresponds to a theoretical removal capacity of 4 molar. So if we're thinking about desalinating seawater, this is actually 10 times higher concentration than we find in seawater. So in principle, these materials present a really great opportunity to utilize the ability to transfer cations between the solid and liquid state for the purpose of desalination. But it had not actually been harvested or such kind of ability had not been fully utilized or is not being fully utilized until recently. So to think about these processes, my group really starts by considering the transport phenomena that's occurring in these systems. When we have an electron transported from an external circuit, together with that, we have a sodium ion transported, and at the scale of an intercalation particle, that induces an electrochemical reaction that causes a change in composition of this intercalation material. So we said, okay, can we model using what's called porous electrode theory, a sodium ion battery, and see if when we flow water through the porous electrodes, is there some substantial degree of desalination that occurs. So what I'm showing here is a model result. The color of the medium inside these electrodes indicates the salt concentration. And what we see is that indeed there's some mild degree of desalination that occurs at the exit of one of the electrodes while we form a brine. But it turns out that if you were to calculate what I would call a Faradaic or charge-based efficiency from this type of battery, it's actually pretty low. And that's because sodium ions are able to transmit between these two electrodes when we use what's called a simple non-selective separator. So we started thinking about how to engineer the process to occur in such a way to maximize the extent of desalination. Firstly, by putting a membrane in between the two electrodes that would block the sodium transport. While also, since we're not trying to store energy, we're really using it for the purpose of desalination, we can use the same type of electrode material in both electrodes, just having different degrees of sodium intercalation. That is, one electrode in an oxidized form, another in a reduced form. And when we do that—
One more minute, Professor Smith.
Yeah, thanks. When we do that, we're able to get a much higher Faradaic efficiency and actually get substantial degrees of desalination. I will skip this slide, just say that this is really my entrance into this field. We're doing a lot of things in this space now. And in particular, in some of our most recent work, we've shown that we can desalinate brackish water with only 25% more energy consumption than thermodynamic minimum. So if you revisit that plot that I showed at the beginning of my slides, we're right near the thermodynamic limit, which is really exciting. We're moving toward higher salinity feeds based on what we've learned in this regard. And I'm very excited to find opportunities to collaborate with folks from UNAM. So thank you, and I'll leave it there.
Thank you so much for that interesting presentation, Professor Smith. And would
Dr. Armando Gonzalez, please start your presentation.
Yeah, I'm sorry. I was in the first session and I couldn't go here, but yeah. Well, yeah, thank you so much for your assistance and thank you for the invitation as well. My name is Armando Gonzalez Sanchez. I'm PhD in chemical engineering, and I work at the Engineering Institute of UNAM as researcher. I'm going to present one of my research topic at the Engineering Institute, the biogas purification and its use. Well, first of all, I need to define what is biogas. Biogas is defined as a gaseous mixing of several gases, which is produced from the organic matter decomposition through anaerobic digestion. Its composition is variable and highly dependent on the waste origin and type of treatment installations. Here, so an important component of biogas is methane, which stores chemical energy, and it can be further utilized to generate heat and work. However, there are other undesirable components like carbon dioxide, oxygen, and hydrogen sulfide, which can limit its use. But why should be the biogas purified before its use? Well, here, methane is the highest viable component of the biogas, as I told you before. Therefore, the rest of components promotes undesirable effects when biogas is not purified and utilized as combustible. In example, the CO2 and nitrogen reduce the calorific power of biogas, not only by dilution. The oxygen contained in biogas provokes corrosion in tubes and storage. Another undesirable components is because they dilute the methane concentration can be considered hydrogen and carbon monoxide. And the most problematic components like hydrogen sulfide and others like ammonia and allocarbonates induce corrosion in tubes, compressors, and engines. And the others depends of the origin. Siloxanes can also generate clogging of tubes and can provoke several damage in engines. Well, there are several purification technologies based on physicochemical and biological principles, which can be deployed as a function of biogas final use. In Mexico, I'm going to talk about Mexico. Normally, the biogas utilization is limited as an energy source because it's high H2S content, which could destroy the initial and high initial investment that normally is performed by authorities and some companies. And recently, looking for alternative energy non-fossil fuels, the crude biogas could be highly purified and converted to biomethane, which composition is similar to natural gas. So I'm going to focus my presentation and rapidly to comment some experience about my group at the Engineering Institute regarding to the removal of H2S and CO2, deploying biotechnological processes. The first one is the H2S removal from biogas, deploying an aerobic process, which consists of, at the first stage, in the absorption unit with chemical reaction, where the H2S react with hydroxide ions, and then further high pH, then this process consumes the hydrogen ions, and dropping the pH, which is further increased in the aerobic reactor. And then, but also by controlling the air supply, we can produce elemental sulfur, which can regenerate the hydroxide ions consumed in the absorption column. Then this process it has been assimilated in our group since lab scale and scale up to full scale applications. For example, like the case one, and we deploy this process in a full-scale biogas desulfurization plant in Santiago de Chile, where I saw that one of the people are from Chile also as well. It was installed in the surrounding neighbors of Santiago, where there is installed a beer factory. There, the factory produces biogas in high amounts, but with high amounts also of hydrogen sulfide. Well, we deployed a treatment process called biological desulfurization with elemental sulfur. The biogas was used by the company to produce in situ power and heat generation for the beer production processes. Besides, the elemental sulfur could be used for production of sulfuric acid, salt improvers, and why not in the possible manufacture of sulfur lamps? It's a future use of this sulfur. In the other side, the second one that I want to present is the simultaneous removal of hydrogen sulfide and carbon dioxide from biogas, deploying a photosynthetic aerobic processes, which consists at the first stage in the absorption column with a chemical reaction of H2S and CO2 is performed also under high pH values. Then the H2S, once solubilized, is the carbon dioxide by microalgae is fixed by photosynthetic reactions, producing oxygen, where the oxygen is obtaken by sulfide oxidizing bacteria to oxidize the H2S, mainly to sulfate. One of the advantage of this process that we use only effluents from the anaerobic digestion process, also from the other organic wastes like digestate, and recently we explored the use of lixiviate or lynched from the organic fraction of wastes.
2 minutes left, please.
Okay, then the second, and then this is the process that we deployed. As I told you, the one unit is the absorption column, and the other one is a lagoon, where the photosynthetic reactions are performed. Before producing methane, biomethane, which is stored and injected possible in the natural grid network. Then we apply this process also in a full-scale application here in Jalisco, Mexico, in San Juan de los Lagos, where we install a full-scale scrubber where we treat 10 meters per hour of biogas to remove H2S concentration in these amounts, and also we remove the CO2. In this process, we apply the photosynthetic biogas upgrading process, recovering biogas. Then the company use the power and heat generation, and they are using the pigments and the microalgae as a soil improver. And that's all. Thank you for your attention, and gracias por su atención. And see you.
Thank you very much. And then I will ask Dr. Germán Huitrón from the Instituto de Ingeniería to present his work on gaseous biofuels from wastewater and organic wastes. Germán, yes. Please go ahead.
Yes, thank you. I'm sharing my screen. I think you can see now. Is it okay? You can see my presentation?
Yes, we can see, Doctor.
Okay, thank you very much. Well, I'm going to introduce what we are doing in our group about the gaseous biofuels from wastewater and organic wastes. I am working at the Institute of Engineering at the academic unit in Juriquilla in the state of Querétaro. It's in the center of Mexico, this campus, the campus Juriquilla. So the biorefinery of wastewaters, we are working with wastewater and organic waste, and we process it in bioprocesses with the goal to obtain gaseous biofuels, but also treated water and recovery in the way biopolymers as polyhydroxyalkanoates and medium chain carboxylic acids. So the substrates that we use, we are not limited only to this substrate, but the substrates with we are working is with the lactic industry, the acidic cheese whey, that is very, very problematic to treat because of the acidity, and they cannot use to feed animals, for example, what they do with the sweet cheese whey. And another important waste that we use is the winery effluent and wastes. These two substrates are very important to Querétaro, since there is a lot of cheese factory and the production of wine. So in the wine, we use the liquid fraction as well the solid fraction. And we use also the microalgae bacteria aggregates that we form during the treatment of wastewater. And this biomass is used to produce also biofuels. So we worked in biological processes, and in particular, we work in an anaerobic process. And this anaerobic process is, we develop a process to uncouple the fermentation in the first stage and the methanization in the second stage. So in the first stage, we obtain hydrogen, and in the second stage, we obtain methane. This configuration has a lot of practical ways, for instance, to treat the acidic waste that we use, and to produce hydrogen and other products. So we have treated waters. We have been working in lab scale, but also the scaling up of this process in a pilot plant. In the case of hydrogen, we obtain also in the first stage carboxylic acids, and this carboxylic acid we can use in photofermentation on bioelectrochemical systems to produce more hydrogen, to extract all the hydrogen that is present in the wastewater. So in this case also we have been scale up the process from lab to pilot scale. Here we have achieved very interesting productivities, about 10 liters of hydrogen per liter of reactor per day. The Department of Energy has put as a goal to obtain 20 liters per liter per day. So we are very close to obtain that by the configuration of dark fermentation and bioelectrochemical systems. So it's very promising to treat the wastes, but also to obtain some value-added products during that. In the case of this acidogenic stage, when we obtain hydrogen, we also work for the production of carboxylic acids. That is, that are medium chain carboxylic acids as caproic and octanoic acids that have a better price in the industry than acetic, propionic, and butyric that are commonly produced during this stage of the fermentation. So in this case, we studied with the residual of the winery industry, because to produce these carboxylic acids, there is an elongation change that needs acetate and ethanol. And the acetate and ethanol are present in the winery waste, and in the solid part also the lees that are produced, rejected is the after they pressed the grapes, there is a solid that we can also ferment and to produce this acetic acid. So in the reactor here, this is the process. This is the main reactor. We have a system of membranes to separate, and in the reactor we achieve to have, depending on the condition, 7 to 10 grams of caprylate or caproate, hexanoic or octanoic acid. But after the purification with the membranes, we achieve to have 36 grams of caproate per liter of these acetic acids. And with that chain acetic acids, we also work with purple nose bacteria with a native mixed culture to produce polyhydroxyalkanoate, the bioplastics, 5-aminolevulinic acid, that is a complement to the agriculture, is used, this product in agriculture to protect the plants against disease, and coenzyme, Q10 coenzyme and pigments. So in this way, this is our biorefinery concept. As I tell you, we use winery effluents of cheese whey effluents as an example, but it's applicable to a lot of things, or microalgae biomass. And in the first stage, in the acidogenic reactor, we obtain hydrogen, and with the products of the first stage, we can obtain volatile fatty acid, medium chain carboxylic acid, or polyhydroxyalkanoates, biopolymers. And the residue of that, we pass to another reactor to obtain methane. So we can obtain from the effluents, the waste and water and effluents, hydrogen, methane, and value-added products. And of course, because this is our goal, treated water and reduction of the waste that are produced. So thank you very much. I like to thank also the biofuels cluster that was supported a lot of this research, is the Secretary of Energy of Mexico, CONACYT, and all the students of my group that are working, Sharon Eduardo in the medium chain fatty acids, in the polyhydroxyalkanoate, Roberto, Agustin, Virginia, microalgae, Marcos, Enrique, Daniela, and Daniel and Eder in hydrogen production. Well, thank you very much.
Thank you very much, Dr. Huitron. And we will listen now to Ms. Martina del Cerro from the University of Illinois. She will be presenting the work entitled Improving the Productivity and Performance of Large-Scale Integrated Algal System for Wastewater Treatment and Biofuel Production. Please go ahead.
Can you see my screen now?
We do.
Yes. All right, so good morning, everyone. My name is Martina del Cerro. I work at the Illinois Sustainable Technology Center. And as you recently introduced, I'm going to be presenting the project I manage that's funded by the US Department of Energy called Improving the Productivity and Large-Scale and Performance of Large-Scale Integrated Algal Systems for Wastewater Treatment and Biofuel Production. So just to provide you with a little bit more of context of who we are here at the Illinois Sustainable Technology Center, we're an applied research institution developing research in three main core areas, which are energy, waste utilization, and pollutants. We also have an outreach program, that's our technical assistance program. And in recent years, we have been very successful in getting projects funded and, well, securing funding. Just between 2018 and 2020, we received more than $84 million in external funding. Our major partners include the US Department of Energy, the US EPA, and the state of Illinois. So the topic I'm going to be talking about today, I've sort of located it at the intersection of energy and waste utilization, since I'm going to be talking about these algal systems that we're developing for wastewater treatment and biofuel production. So to provide you with even a little bit more of context, like I said, this project is funded by the US Department of Energy and specifically by the Bioenergy Technologies Office, and it's under the Advanced Algal Systems Program, which seeks to lower costs associated to producing algal-based biofuels and products. So this program is structured into different focus areas, and where this project falls in is at the system integration. So basically, we are testing all these other developments at the field and validating all these improvements and collecting meaningful and relevant data to further leverage all these technologies. So this project by itself has received $4 million in funding between cost shares and funds from the US Department of Energy. And from now on, you'll probably hear me refer to it as the SIPA project, since it fell under the funding opportunity announcement titled Cultivation Intensification Processes for Algae. So with that introduction, I'm going to dive into the details of what we do here and what the main goal of this project is. What we're doing is mainly leveraging an existing wastewater treatment for biofuel production. And this technology is called the algae wheel, which is a rotating algal contactor, and it's also an ultra-low energy technology. So basically, the pictures you're seeing here are the 4 tanks of algae wheels that we have in our pilot installation here at ISTC, and they're all operating in parallel, and any visual differences that you might perceive in them are actually correspond to different treatments that we are applying in them to achieve different results. So how does this technology work? So basically, air is fed to the tanks through perforated tubes that are located underneath the wheels, and that makes the wheels turn between 1 and 2 RPMs. So here on the wheel paddles, we have algae growing and phototrophic bacteria, and at the same time, there's MBBR, so moving bed bioreactor media inside these wheels that act as a support for bacterial growth. So we developed this symbiotic relationships between organisms that ultimately lead to a very efficient system in treating wastewater. But in this project, what we're trying to do is further leveraging its use to produce biofuels and maximizing biomass productivity and enhancing oil quality. The different strategies that we're using or that we're trying out to accomplish this are endoreduplication, which basically means not allowing the cells to go through mitosis, but rather increasing their DNA content and grow larger. Bioaugmentation, so inoculating other bacterial species into the system, which are known to induce effects that enhance growth. Modifying process parameters, such as adjusting the spin rate according to light intensity, for example, modifying the system temperature and adjusting the harvesting frequency, adding adsorbents for retention of growth resources that once absorbed can be released back into the system and keep those productivities higher. And finally, all this, again, will come together. All the measurements that proved most successful will be demonstrated in full-scale algae wheel installations. And we are also performing interim techno-economic analysis and life cycle assessments. So what are the different steps involved at all stages in this process? We have the harvesting of this biomass that occurs at our pilot here at ISTC, which involves a series of steps which ultimately lead to a final clarification step where we obtain a biomass sludge and then an aqueous phase that's also rich in biomass that we sample and take for further analysis. The sludges are collected and after an initial dewatering step, we convert them into biocrude through hydrothermal liquefaction, or HTL, which is basically a process that's advantageous compared to other conversion processes because we don't need the feedstocks to be completely dry. So at very high temperature and pressure, we induce a depolymerization reaction of those feedstocks and obtain the biocrude and then an aqueous phase that's also rich in other compounds. And I'm going to talk briefly about this in a few moments. So this is the bench scale HTL reactor that we have here at ISTC that we've been running our preliminary tests. And our goal in the future is to scale it up and even process all the biomass that we collect from our pilot in this mobile HTL setup, which is basically a pilot installation, but we call it mobile because it's set up in a trailer that we can just transport to different sites. So like I said, in this HTL process, what we obtain is a biocrude and then an aqueous product, but that it's still rich in compounds that were really hard for us to obtain through the whole process, like organics that serve to produce this biocrude and nutrients that, are mainly nitrogen species that we don't want them to end up in our biocrude, basically because combustion of these products would eventually lead to the release of NOx gases. So the way we separate this to reclaim the organics are through a membrane filtration step. And as you can see here to the right, this is our feed, this is our aqueous HTL product, this is our concentrated retentate or our concentrated product that has lots of organics, and this is our permeate. So that's very basically depleted of all the organics. And so we can recycle these streams or use them valorize them for other purposes. And then the biocrude, as you probably know, needs to be upgraded. And that's the hydrotreating step that I've added here at the bottom. So how do we keep track of how successful all these different steps that we take in our pilots are? Well, we monitor our biomass activity through to dissolved oxygen measurements. Here to the right, this is simply a graph for you to get a sense of how we track that dissolved oxygen in our tanks. Like the variation is due to, like I said, all the different treatments that are currently being applied to them. And then we also monitor our pH. And then to quantify the amount of biomass that we are producing, and again, like the success of the different measures, we monitor productivity through measurement of total and volatile solids, which also gives us an estimation of the ash content of that biomass. One of the goals in this project is to reduce the ash content of the biomass, because that way we will be increasing our biocrude oil quality in the end. And of course, we must not lose focus of the main goal of the system, or the main idea for which it was firstly conceived, which is to treat wastewater. So we also keep a very thorough water quality monitoring and assess parameters such as effluent COD, ammonia, and total nitrogen.
2 minutes left.
Yes, so basically I had like some further findings in this project to share with you, but like for the sake of time, I decided to just cut it here. So I can either carry on, or if you have questions, I can stop here.
We appreciate the work you showed, but also the timing. We have like 2 minutes for any questions. And also, if you don't have time for questions, please place your questions and answers at the chat, as somebody is already doing that. Any questions from Ms. Martina del Cerro, or comments? I guess I do have one. Is this unit already commercially available? I mean, if somebody in Mexico, like a city or a company will be interested, is this already available?
Yes. there are several algae wheel installations deployed across the United States. So the full-scale facilities are totally operational right now. It's a technology that if you log in online, you can get all the details. And we actually work with them for our full-scale implementation, which should take place in about a year.
Okay, sounds like you have a very, very solid piece of work and technology. And let me then ask you the question then, how do you see a potential interaction with other colleagues at Illinois and also in Mexico? What will you say that there is an opportunity to add some technology to what you already have?
So we're always looking for collaborations that are like different, like there are definitely lots of lines of research that can span from the kind of work that we do here, mainly concerning the biocrude conversion processes, or even everything that happens here in the pilot, like the biomass adapt very quickly, I dare say, to different conditions and different environments. So each of our tanks is unique in terms of the biomass that's growing there and the kind of treatment that is going on. So like I said, any biomass characterization or anything that can span from that that finds application in these different strains would be beneficial to us if it eventually leads to increasing productivity, which is in the end what the U.S. Department of Energy is seeking for right now, to boost algal systems productivities at the moment. So yeah, anything that can contribute to that would be more than welcome, and we're more than open to collaborate.
Thank you very much. And then we move on with our program. It's the turn of Dr. Simón González Martínez from the Institute of Engineering of UNAM, and he will be presenting his work, Local Feedstock for Biofuels. Please go on.
Sorry for this lab. Well, I'm Simón González from the Institute of Engineering at the UNAM, and I will just explain how happy we were for the last few years about fermentation and methane production from municipal and agricultural solid wastes and energy crops. Let me just play this this way. Okay. This whole project began some years ago because funded by the government of Mexico City. They have the need just to make proposals to how to treat the municipal solid waste. So they gave us this project, and we made some characterizations and made some proposals. So I am just going to refer briefly to some examples. Mexico City has fractions, the wastes of Mexico City have fractions, and about 70% it's vegetable wastes, non-identifiable garden wastes, fresh garden trimmings and fruits. Mexico City accept garden trimmings as organic waste, differently from other countries which do not accept them. And then we found out that, for example, the organic solid waste produces about 350 liters per kilogram volatile solid, but kitchen paper, garden trimmings, and waste fruits produce more. So we made a proposal on how to manage the wastes in order to just to avoid, for example, fallen leaves and some unsorted and other wastes that come together with the organic solid waste. So what have we right now and projects running? We have, for example, acid fermentation of organic urban solid wastes for further biogas production. We have found over the last few years that there are several intermediates such as ethanol and lactic acid who are not affected by the partial hydrogen pressure. And we now are aiming at doing a fermentation of the wastes previously to methanization, because this can produce more methane than just the fermentation or methanization of the wastes. Ethanol and methane production from the organic fraction of organic solid waste. So we are working on production of ethanol from the organic solid waste. This is possible, and we have found that with a little manipulation of the process, we can produce quite ethanol quantities. There's another project going on salt restoration using digestates from the anaerobic digestion. And this is just a test, a pilot study on how the digestate from the digestion of organic solid waste can help restore soils. We are working also on the continuous production of volatile fatty acids and alcohols from the organic fraction of urban solid wastes. There's very few information in literature about the production of alcohols, continuous production of alcohols from wastes. And then we are also working on a biogas and other byproducts from the fermentation and aerobic digestion of the cacao processing solid wastes. This is a project that has just started, and we already have some interesting or producers in Tabasco who are interested in continuing this project. So just I looked at the what the University of Illinois is doing right now, and I just saw they have interests in energy crops for the production of biofuels. So we are proposing internally, and hopefully somebody has interest in just making or just to come with this project to the biorefinery of nopal, so Opuntia species, for ethanol and biogas production. There's a lot of research in Mexico about this plant, which is a very interesting plant, but very few are just serious studies just to see how ethanol and biogas can be produced from them in a very, say, academic and production fashion. There is also sweet sorghum for ethanol. In the United States, sweet sorghum is largely produced. That's probably the largest world producer of sweet sorghum for ethanol, but there is few information about the biogas production from this plant. And there is also a very interesting plant which has been used for a long time, raps or canola, and for ethanol and biogas production. Most of it is used to produce oil for human consumption, but the stems are rich in starch, and few information is available about the production of methane from raps.
2 minutes left.
And then we have another one, biogas production from the cacao processing wastes. I already explained this. And the selective production of ethanol and lactic acid from the organic solid waste is a very ongoing in research, and we have to make it a larger project. And the least development of a device for automatic biogas measurements. We use these devices a lot, and we would like to increase, well, to reduce the cost of buying several of them. And we have produced, these are 16 papers in prestigious journals, 37 in proceedings, in international conferences, and so on. 3 graduated doctors and 9 graduated MSc students, all with research theses and so on. So this is everything I have to say at the moment. Thank you very much.
Thank you very much. We have 1 minute for any question or comment. I do have one question. Apart from the government of Mexico City, have you been approached by any private company to take advantage of your technologies?
No, unfortunately not yet, because these are just new projects. We are promoting them, and no, we have not. And you know, the pandemic situation the last 2 years have been very stressful and stopped all efforts to make contact with other parties.
Thank you very much. Now I will ask Dr. James L. Best from the University of Illinois to present his work, Sedimentary Heterogeneity in Subsurface Sandstone Reservoirs. Please go ahead.
You're muted, sir.
Thank you very much. My name is Jim Best. I work at the departments of Geology, Geography, and Civil Environmental, and also Mechanical Science and Engineering at Illinois. And what I'd like to do today is just show you an outline of our work looking at the heterogeneity in subsurface sandstone reservoirs. So this may be a little bit of an outlier to some of the work that we've heard already today. The broad outline to our work is to try and understand the geological controls on the movement of fluid through sandstone reservoirs. So this could be oil or gas or water, and increasingly these applications have been in the sequestration of carbon dioxide. And some of the work that I'll illustrate today has concerned some really large projects that have been led by the Illinois State Geological Survey. And the broad background to this is the need to understand the flow of fluids within sandstone reservoirs in the subsurface from a large scale, from a scale of hundreds of kilometers, down to scales that are of the order of millimeters or less that concern grain size and pore space. The specific questions that we've been looking at are: what are the scales of the different heterogeneity, variety, and sedimentary properties that control fluid movement? What scales are those different heterogeneities present at? And how can we use those scales and model them for looking at the prediction of movement of carbon dioxide, oil, and gas within subsurface reservoirs? And again, we're looking at a whole range of different scales here and different data sets. Our approach has been to use the study of both modern environments to quantify sedimentary environments and their characteristics, and then integrate that with a study of rocks and the ancient sequences to build up a quantitative model of heterogeneity and how that can be used in modeling and predicting fluid movement. So that's the general approach. In the modern, what we've been doing is studying a whole range of different environments in different sedimentary sequences, so rivers, lakes, oceans, where we've been using a range of techniques such as multi-beam acoustic sounders to look at the form and shape of the river bottom or the lake bottom. We've been then using geophysical techniques such as ground penetrating radar to characterize the nature of the subsurface sediments, and then ground truthing that with techniques such as coring to look at the properties of those sediments in these different modern sedimentary environments. And the type of data that we get out are data such as the form, the bathymetry of the modern environments. This is a bottom of the Columbia River in the Pacific Northwest. We're looking at coring to look at grain size variations. And we're using these techniques such as ground penetrating radar to look at the structure of subsurface deposits. So that's the modern. What we're also doing is using study of ancient sediments in both cores that are taken down through these sequences, as well as outcrops. This is an outcrop in Western Ireland, looking at a range of different sediments. And here we can look at the three-dimensional shape and architecture of these sediments. We can increasingly use techniques such as drone photography to reconstruct their three-dimensional shape and internal characteristics. And then what we're able to do is ally this sort of study of ancient outcrops with study of core, and then also study of thin sections. So we're looking at the ancient sediments across a range of scales, through from kilometer scale, where we're looking at a variation in, for instance, the sandstones that here are interbedded and intercalated with a range of much finer mudstones, and look at the geometry and internal characteristics of these sediments. So that's our general approach, is to try and merge study of modern environments with a study and characterization of ancient sediments. But that, I must stress, that's across a whole range of scales, from pore scale right through to entire sedimentary base scale. Just as an example, as the application of this, this is a project that we've been involved in with colleagues. It's been driven by work down at the Illinois State Geological Survey over the last 6-10 years. Where they've been looking at a whole range of projects looking at CO2 sequestration for carbon capture and storage. One of these involving a project in Decatur in Illinois, which is so far involved the largest test case of injection of CO2 into the subsurface. And what we're seeking to do here is to look at the suitability of subsurface reservoirs for the storage of CO2. And to do this, we need to look at the heterogeneity, the variability in these reservoirs, and how we can use that to model the flow of CO2. And integral to that is actually looking at the porosity and permeability of sediments and how that links back to 3D and how we can predict that. So what we've been doing is using this combined study of modern and ancient environments together with this case study Illinois to provide a characterization of the shape, size, and internal characteristics of these sediments, which are being used as a test case for CO2 sequestration. And I should say there's a whole range of projects within the university and the Illinois State Geological Survey that are still pursuing this in terms of carbon capture and storage, but also enhanced production from existing hydrocarbon reservoirs. One example of this is a study at this Decatur test site for CO2 sequestration that is storing CO2 in Cambrian age, 500 million year old sediments, and a whole series of very suitable sandstones in the subsurface. So what we've been part of is a very large project, and our role has been looking at the sedimentary characteristics. And simply what we've sought to do here is to use a whole range of subsurface data, core data principally, along with a whole range of subsurface geophysical information, to characterize the different sediments that are present and use our knowledge of modern environments and ancient sediments to build these up into a 3D model. And this is just a cartoon schematization of this, of the different sedimentary environments that are present. And in these old sediments, and these are sediments that were deposited actually before land plants had even evolved. So we're looking at a very different Earth surface here than we actually currently have in many places. We've got a whole mixture of sediments from rivers to the beaches, to Aeolian desert dunes, through to beach ridges and shallow marine environments. And what we've been able to do is to characterize the different building blocks, the different compartments in which these which comprise these sandstones, to begin to look at the relationships between porosity and permeability, and to show how they vary between these different units. And importantly then, what the shape and size and connectivity of these units are, because that what will determine to a large extent how CO2 flows through these reservoirs as carbon dioxide is injected. So we've been using our bring in this model.
Please mute your microphones. The person
who is talking, can you mute yourself?
Thank you. I'll try and continue. Hope you can hear me. What we're also able to do detail this at a smaller scale. So with colleagues across at Wright State University, we've been taking this same approach, but using this to look at different types of cementation that are occurring within the reservoir. So originally these sandstones would be perhaps very porous, but during their geological evolution, they get precipitates of here calcium carbonate within the sediments that change their porosity and permeability. So we've also been able to team this approach of looking at outcrop with looking at core, with looking at this different characterization of sediments, to look and see how these cements, these calcium carbonate deposits that occur within the subsurface reservoir, how they affect both the permeability of flow through the reservoir, and how we can build that into geocellular models to better characterize the flow of CO2 through these reservoirs. So finally, just a summary, our approach has been to try and link the present and study of the present with the past, to link modern environments, and this is a sort of environment in a dry, arid Aeolian landscape. This is actually the Namibian Sand Sea in southwest Namibia. This is a good parallel in some ways to part of the work looking at this subsurface 500-million-year-old reservoir in western Illinois. And we're using that not only to look at the present as a key to the past, but also use our characterization of ancient sediments to help us look at actually future scenarios of environments in climate change. So this whole approach is about using this to unlock and quantify reservoir heterogeneity and its use in predicting CO2 and other fluid movement through subsurface reservoirs. Thank you very much. Thank you, Victor.
Thank you very much, Jim. Are there any questions for Dr. Best? Jim, very interesting work, and I have a couple of questions. The first one is about the resolution, the spatial resolution of the images you show. Could you comment a little on that?
Yeah, I could. So one good point is that the scale that we're studying is from the pore scale, which is millimeters and down to microns, through to basinal scale, which is hundreds of kilometers. One thing, of course, we have when we're looking at subsurface data is we often have a scarcity of data. So we may only have a few wells or cores that penetrate the reservoir. And so one of the beauties about this approach is what we're trying to do is give a better predictability in 3D, where we've got sparse data, by using other data in either modern environments or ancient analog sediments to enable us to look at a better spatial resolution than we actually have in the field that we're studying. So often we're trying to use other techniques to fill in the lack for sparse data, scarce data, with these other alternative approaches looking at modern and ancient and analogous environments.
Thank you. And related to that question, since you have such a wide range of scales and sizes, have you done any work on scaling? I mean, related to fractality of the system?
Yes, in part. So yeah, that's a very good question. So in terms of, say, looking at a small river versus a large river, yes, we've done some work actually looking at the scaling of different components of those environments and how they scale up through to larger systems. So in terms of the sedimentary environment, for some of these, yes, we have. And the answer is some of those things seem to scale across different scales of, for instance, river channel. Other things are definitely scale specific. And so again, a key to that is identifying, for instance, things like the size of the channel or the size of the desert conditions that we're looking at in the ancient sediments, so that we can apply or not apply those scaling relationships.
Thank you very much.
Thank you.
If are no further questions for Dr. Best or other of the presenters, I guess we have like 7 minutes to go and grab a cup of coffee. And please be back on time at 10:25, please. We will leave everything open. Just turn off mics and videos, and we will resume in 7 minutes, please.
All right.
Thank you.
Thank you very much.
from the Institute of Engineering of UNAM. He will be presenting the work entitled Production of Bioelectricity Coupled to Ammonium Oxidation. Please go ahead.
Thank you very much, Professor Castaño, and thanks for organizing this interesting symposium. As you already mentioned, this is the title of my presentation, basically focused on finding a new technology to remove ammonium from wastewater. Let me see here. But in the context, we have that the main environmental problems associated to nitrogen pollution are mainly eutrophication and acidification of water reservoirs, as well as greenhouse gases emission and death of aquatic organisms. And as you know, the main nitrogenous species that you can find in wastewater is ammonium. And traditionally, ammonium has been removed from wastewater by combining the nitrification and the denitrification process in different reactor configurations and arrangements. And lately, the I-MMAS process was introduced because combined with partial nitrification, you can also achieve the ammonium removal from wastewater. The I-MMAS process comprise the anaerobic ammonium oxidation with nitrite as terminal electron acceptor, and then you have the nitrogen gas as the main product out of this reaction with a small fraction of nitrate coming out from the partial oxidation of nitrite to nitrate. But mostly is converted to the nitrogen gas. And if you compare with the traditional nitrification and denitrification process, there are a couple of big advantages of introducing the I-MMAS process to remove ammonium from wastewater. Basically, because you have a huge saving of energy, because you don't need to oxidize ammonia to nitrate completely. And the second advantage is that if you are dealing with autotrophic microorganisms, then you produce less amount of sludge that then you have to dispose of the wastewater treatment plant. So these are the main advantages, but still you need to achieve partial oxidation of ammonia in order to get nitrite and to proceed with the I-MMAS process. So we have been working on alternative electron acceptors to achieve ammonium oxidation and to apply it in wastewater treatment. And we found that the I-MMAS process can proceed also linked to the reduction of sulfate and ferric iron in marine sediments. As you can see here, how the consumption of ammonium is connected to the reduction of this electron acceptor, which, by the way, is the main electron acceptor in marine environments. So ecologically, it plays a key role on nitrogen loss in marine environments. And we call this name sulfamox. And we also found that the same marine sediments are able to perform ammonium oxidation connected to the reduction of ferric iron, as you can see in this graph. So talking about the applications of the sulfamox process, this is relevant for wastewaters with a large content of ammonia and sulfates, such as those coming out from aquaculture and seafood effluents, you know. Later, we also found interesting results related to the I-MMAS process linked to the microbial reduction of natural organic matter, particularly the humic fraction of the natural organic matter present in sediments. You can see here how the consumption of ammonia was also connected to this reduction of natural organic matter. And what is involved here is that electron accepting functional groups present in the humic substances are accepting the electrons coming from the oxidation of ammonium. And so in this way, you have a certain oxidizing capacity in the system. As you can see in this infrared evidence, During the course of ammonium oxidation, these quinone groups were reduced to phenolic groups here. And making an electron balance, we found that up to 99% of the electrons coming from ammonium oxidation was coupled to the reduction of these oxygenated functional groups in humic substances. Interesting that more or less at the same time, there was a somehow related study published by this group because also quinone groups and other oxygenated functional groups are also present not only in humic substances, but also in graphene-based materials. And they found that ammonium oxidation was coupled to the reduction of graphene oxides. And they documented this by Raman spectroscopy. And they also found that hydroxylamine and hydrazine were key intermediates during the course of ammonium oxidation to the nitrogen gas. So there is a huge potential to achieve ammonium oxidation present in many types of wastewater. For instance, you can think on wastewaters coming from piggery farms or in industries processing a lot of proteins. So ammonia is coming from the hydrolysis of proteins, and they need to remove because of the toxicity of these pollutants. So the big news here is that we don't need partial nitrification anymore, because you can consider the anode of a bioelectrochemical system, which is mainly composed of graphitic material, to fuel the oxidation of ammonium connected to bioelectricity production in the system. So there have been already a few works on this issue, and certainly the amount of energy which is needed to run these bioelectrochemical systems is lower than the energy demanded by the traditional nitrification and denitrification process. But still, we need a lot to do to improve the energy yield in these systems. And in our horizon, we have the following strategies that we are currently exploring. We want to perform doping of our electrodes with catalytic nanoparticles, particularly palladium and platinum, to boost still the energy yield that you could expect in this bioelectrochemical system to achieve ammonium oxidation. Also, another strategy we're interested on is to connect this I-MMAS process in the bioelectrochemical system to degrade emerging contaminants, for instance, antiviral agents currently applied for COVID. So the goal of this project is to achieve a bioelectrochemical system with a net energy production linked to ammonium oxidation. And that's what we're interested on this project. So thank you very much for your attention.
Thank you very much. Are there any questions or comments from the audience?
I have a question.
Yes, please, go ahead.
Francisco, very interesting presentation. So when you think about electrocatalysts, I mean, it's a difficult problem, right? Because you need to create a nitrogen-nitrogen bond, even though you have some of that discussion about hydrazine being an intermediate. So that's a tough problem, but it's a tough problem that is being addressed right now with other types of catalysts, like for instance, for carbon dioxide electroreduction, there's a lot of talk about how do you make C2+ products, right? And so you need to have adjacent sites that can make that bond. I mean, we'd be interested. I mean, we have tools for combinatorial screening of electrocatalysts and things of the sort, but I'm wondering if you have started already something in that direction, or if you're interested at all.
Well, not yet, because currently we are exploring different inocula from sludges coming from wastewater treatment plants in order to test the capacity to oxidize ammonia, for instance, with mobile elements like graphene oxides or humic substances. because the principle is the same to apply it in the bioelectrochemical system, right? So we are in that stage at the moment. We just started with the project, but of course the goal is to apply the concept in the bioelectrochemical system in which you optimize the energy production, as I mentioned, by, for instance, doping the electrodes with these nanoparticles, metallic nanoparticles, right? But thank you. I think you're right. There is also a huge interest on bioelectrochemical systems also to take the advantage of removing CO2 also, yeah.
Okay. Thank you very much. Now I'll ask Dr. Hailin Xiao from the Institute of Renewable Energies of UNAM to present her work overview of photovoltaic research activities in the Institute of Renewable Energies. Please go ahead.
Oh, thank you, Professor Castaño. Thank you, everybody. Good morning. I'm going to talk a little bit different topic, which is in solar cell research in the Renewable Energy Institute of UNAM. Sorry. Oh, can I just a little minute? My mouse. What is the problem? All right. I will stop and start again. Sorry. Yeah. A solar cell is an electronic device which converts the light to electricity. It consists basically on
excuse me, we are not looking at your presentation.
Oh, sorry. So, yes, yeah, I know the problem.
Now it is. Go ahead.
Yes, then the solar cell is consists basically in an active layer, which is semiconductor. It can be a couple of layers, then two metal contacts. And when you light the solar cell, you will generate, the device will generate or convert the light into electricity. So the efficiency can be measured by lighting the cells, and you measure the current as a function of voltage. And the value of voltage at open circuit, current and the short circuit, and fill factor determine the efficiency of the solar cell. The most commercially available photovoltaic solar panels are based on silicon technology. And these technologies are high energy consumption based and very expensive equipment that usually they just produce in a couple of countries. And there are another technology available, which also are commercially products like thin film solar panel based on cadmium sulfide, cadmium selenide. And these are also based on high temperature, high vacuum systems. The third generation, which I'm going to talk about a little bit, or also called emergent solar cells, they are under research. That is to say, there's no commercial products. They basically by they made by chemical solution deposition methods. They use less energy, and the technology less printing, plastic industry can be used to produce these kind of solar cells. In our institute, there are a lot of research work on solution deposition of semiconductor thin films which are metal chalcogenized thin films, and many of them can be used as active layer, which means they can absorb the light. Others are transparent conductive materials, which can be formed and to help increase the efficiency of the solar cell. And some of them are very promising materials for low-cost emerging solar cells. Recently, during the last 10 years, the best emerging solar cells are found in perovskite structured materials. In 2021, the efficiency record in perovskite solar cell is higher than 25%, but in small areas and manufactured under inert condition, which means that's inside the glove box filled with nitrogen gas. The structure of a perovskite solar cell consists in a transparent glass substrate, then an electron transport layer, an active layer, perovskite, which basically absorb the light. Sorry, okay, I get it later on. Then a whole transport layer and metal contact. The whole transport layer is to improve the efficiency. The chemical structure of perovskite solar cell, which show a very good photovoltaic properties, are based on one organic cation and one divalent metal cation and 3 halide ions. This is the structure of hybrid perovskite. But there are very challenging problems with perovskite solar cell. One of them is its instability in high relative humidity, under oxygen ambient, high temperature, and the UV radiation, toxicity, etc. So in our institute, during the last 7 years, we are working on the perovskite solar cell, but we try to prepare these film very sensitive to humidity in ambient condition, because we don't have a good glove box. This glove box we have cannot circulating constantly the nitrogen gas. That's why there's no use to prepare a very high efficiency and prescription of the best laboratory in the world. So we are trying to prepare perovskite or the thin film under relative humidity between 40 and 60%, which is our condition in México models. The manufacturing of perovskite solar cell consists of several steps. First, you have to clean very well the glass substrate, then etching, chemical etching, some part of them to make an active area. The first deposition is the electron layer, the electron transport layer. Then the second is the perovskite film. And the third one is a whole transport layer, the 3 by spin coating method. And finally, you can put metal contact by thermal evaporation. The perovskite thin film can be prepared by 2 methods, 1 step or 2 step. In the case, one step which you have every active materials in one solution and you just deposit. In this case, to get a very good property, you have to put anti-solvent to improve the resistivity. And with these hydrophobic molecules, the efficiency is improved under ambient condition. And you can also prepare by two-step method, separating the solution in 2. And we can obtain the nanoporous film to improve the conversion of perovskite and improve the stability. And in the last 3 years, we are trying to get improving the solar cell efficiency from almost 1% to 19%. These are the picture of our device produced. And also we connected a solar cell with a supercapacitor to reach the conversion and storaging in the same step. Conclusion, and it is possible to prepare highly efficient perovskite solar cell under high humidity condition, but we need more collaborations and to improve, to understand the physical chemistry of materials and to improve the stability and the efficiency of these cells. Many thanks to all the students as postdoc and the financial from CONACYT and UNAM, and thank you all for your attention.
Thank you very much. Next presentation is by Dr. Cesar Angeles Camacho from the electromechanical area of the UNAM, and the title is Smart Grid Laboratory and the CU Campus as a Power Living Laboratory. Please go ahead.
Dr. Camacho, you're mute.
Hi, you can listen to me now.
Yes, we do.
Okay, thank you. I will switch off the video because I had a little bad network here. So sorry about. But good morning, everyone. My presentation is about power system. In this case, we are working more in a distribution system. We had a smart grid laboratory, almost new, 2 years old, and we are using the electrical infrastructure for the main campus as a power living laboratory. I think we had a lot of, oh, sorry. What happened? Okay. Why a living laboratory? When, as you know, the campus of the UNAM is one of the largest in the world, probably the largest one. We had more than 300,000 students in the campus. We had almost 400 hectares. And for the electrical infrastructure that we had to supply the energy for more than 200 buildings, we had 5 electrical connections to the national grid. These have 23 kilovolts with 7 main substations. We had more than 200 kilometers for transmission lines in the 23 kilovolts. We had more than 160 power transformers supplying energy to the 200 buildings. We had a capacity installed in the lot, about 70 megawatts, and we had an annual consumption for about 75 gigawatts per hour. But also most important for us is what we had one infrastructure, intelligent or smart one, the PNUs, which are phasor measurement units. It is important because we can have measurements for the phasors, voltage and current phasor, 10 times per second. So it is a very important equipment that we had in the system. And also we had at the state-of-the-art SCADA provide for surveillance one of the largest companies in the world for SCADA for power system and water systems and traffic systems. So using that infrastructure, we had working in some projects. I will mention some of them, the more iconic, I think. The first one is the real-time synchronization monitoring. In this case, as I mentioned you, we had more than 15 this kind of units, and we had measurements for them. And all of them also had information about the PV system that we had in the university, and also for some electrical vehicle chargers that also we had here. We had information for the performance of these equipments, along with the PNUs for voltage and current for the different circuits that we had in the university. This information is sent to the lab. In the lab, we had a NAS where we store all the information for we had right now most than 1 year for this information. So you can imagine the world information that we had about the performance of the electrical power system in the university. But also we had monitoring for the real time. In this case, we can see in real time the different events or faults that we had in the system. And also we had a real-time simulator, which is a machine, a computer machine, where we had some simulation in real time for different equipments, or even for the world system and the iteration with the national grid in Mexico. So this is some kind of one area monitoring, but for distribution systems. The second one is the digital twin of the university medium voltage distribution grid. In this case, we have developed a digital twin using a TAP software, but also we are working now with a different software. The digital twin use all the measurements that we had for the synchrophasor monitoring system, but also for the SCADA system, for the different substations and the feeders, and for the step down substation. So the idea is, with this information in real time, we can perform a digital twin which performs exactly the same as the real one, with the measurement that we had for the real one. Also, we had a human machine interface with the different presentation that we can be in the lab or even for the operation of the system. And also with the digital twin, we can perform real-time or online simulations. We have performed off-the-line simulations and of course post-mortem to identify some faults or the cause of the faults between the university grid and the national grid also. In this case, with the digital twin, we have right now made some simulation in real life simulator. We are also in the energy quality studies to see if this substation had the core grid satisfied. Also, we had some projects planning the integration of new elements to the distribution grid, like PV plants or some kind of fuel cell plants, batteries, etc., to see how is the performance within in the university grid. And also, we had some digital twins, especially for critical loads, like the data center, the integration of the buses, electrical buses, and electrical vehicles to the grid in the university. And in the last time we are talking about is we are working in a state estimation in distribution grid for different to identify events, to identify topological change, etc. The low voltage critical load monitoring system. In this case, we had built out some monitoring systems. For example, for the GETIC, where the UNAM supercomputer is. So we had monitoring the performance of the servers and the computers, and also in low voltage, and also for the 23 volts network. In this case, the information is shown locally for the operators of the building, or the responsibles for the operation of the supercomputer. The information is shown there, or also they can see the information by internet. And then the information is also sent by the internet internal network in the campus to the lab, in this case, the smart grid laboratory that we had, and also to the operators of the university grid to see also the information. So in this case, they don't have to report any faults to the operators. We had severe information for the performance of the computers, of the HVAC systems, the freezing system, etc. And also we had monitoring the electrical vehicle chargers. In this case, the idea is to have different models for different brands of the electrical vehicles and to put all of them in the digital twin to see if the grid can accept all of these charge for different times or different circumstances, etc. And also we had some models for buses right now, and also we want to see if the grid can accept the electrical buses in it. And finally, with the data that we had, we can perform some analysis, some studies using the data. In this case, I can show you, for example, the COVID performance. As you can see, 1 week, some months before the COVID pandemic, and during the pandemic, the performance of the grid. In this case, for example, you can see a large peak. It is because a earthquake in the network. And also you can see right now, for example, the daylight saving time for 2019. In this case, is 1 week before in the winter time and in the summertime. So we can see that we in the university had, in this case, for this kind of buildings, administrative buildings, almost 3–4% the save of the energy for this change in the time. And also, to perform all of these projects, we had some partners, very important partners, I think, technical partners like Survalent One, with this supply with the SCADA, and also some application that we had development had been implemented with the Survalent SCADA to test in a different grids along the world. ETAP, of course, is also a partner. Siemens with the PSSE software. This is the software that use the independent operator in Mexico to perform the operation and planning of the power system. And also we have a collaboration with Dopal in Canada. In the university, we have collaboration with the COAS, which is the coordination of sustainability, for perform some of the studies, the energy saving, something like that, efficient in the buildings. Also, we have collaboration with the operators of the university grid, with the HETIC, as you can saw before, and the unit of planning energy from the Faculty of the Engineering. And also we have collaboration with some universities in the world, with DTU in Dinamarca, and also Berlin, Germany, Arizona State, Michoacán University in Mexico. And we have a strong relation now with the CIFI, the national company in distribution system. They want to test our development projects. And also we see transmission and the national operator, independent operator in Mexico. And also we are part of the SEMIE Oceano and SEMIE grids. So I think we are on time. Thank you very much. That's all for me.
Thank you. Now I will ask Dr. George Gross from University of Illinois to present his work on power and energy systems research at Illinois. Dr. Gross? I don't see Dr. Gross around.
I don't see either.
I haven't seen him the whole morning. Will you agree that we move on with the next presentation by Dr. Maria Teresa Horta Ledesma? And that way we will have more time for questions or for coffee break. Yeah, it's already 4 minutes after his scheduled time. So please, Dr. Maria Teresa Horta Ledesma from the Institute of Engineering, present your work, microalgae biomass cultivated in wastewater for biofuel production. Thank you.
Yes, good morning. Dr. Maria Teresa Horta is not able to be here, so I'm presenting. I'm Rosa Maria Flores, and I'm the Deputy Director of the Hydraulics and Environmental Engineering. Do you see the presentation?
Yep. Yes, please. We see your presentation. Go ahead.
Yes. Okay. Thank you. Well, I think that I can skip this first slide, since we have here something like this in the previous presentations. So I'm going to speak about what they do to produce the microalgae for fuels, biofuels in the group of Dr. Teresa Horta's. And first, they have a first stage where they produce they grow the microalgae in wastewater. Then they harvest the biomass of the microalgae. Then in stage 3, they produce the biofuels, bioethanol, biocrude, biodiesel, and in a further stage, the last stage, they make the intensification of biocompounds, recovery and valorization of residual biomass. And I want to remark on stage 1 that what they do is how they have been managed this is that they got their species of algae from the Texcoco X-Lake area. They are working mainly with 2 species, Desmodesmus and Cenedesmus species. They have been a great success with the production of biomass and biofuels. And they have been working in 2 scales, one in a lab scales and in a pilot scale with a high rate algal pond, which you can see here on the top of the bottom of the page. It's a device of 1.2 cubic meters. And the efficiency, the biomass yields is in the order of 0.5 to 2 grams of total suspended solids per liter, and the efficiencies in the removal of nutrients is high, so it's above 80%, except for phosphates, which is in the order of 43%. And they have also developed the kinetic model that allows them to predict and control the algae cultivation wastewater. Sorry. On step 2, once they have the biomass of microalgae, one of the problems is how to separate the biomass from the treated wastewater. And what they did is that they have a patent with an ozone flotation device, which you can see on the right. And this have make a very good biomass recovery. They have more than 80% of biomass recovery. And the concentration of biomass is high also. You can see here 23 grams of total suspended solids per liter. And lipids, carbohydrates, and proteins are also in a very good quantities. And the ozone permits a very high extraction of lipids, so the production of biofuels is improved. And they have also been working with a sedimentation device, which you can see on the bottom of the slide. And they have been making some experiments with that also. Once they have separated the biomass from the wastewater, they have now are able to produce the biofuels. They can produce biocrude, bioethanol, or biodiesel. For the biocrude production, they use the catalytic hydrothermal liquefaction process, and it permits very high calorific power, and the characteristics are improved when compared with the conventional processes. For example, they produce less greenhouse gases, like the production of carbon dioxide is 1/3 than the one with the conventional process. And the net energetic ratio is 2.7. It's not as high as with the conventional process, but it's not bad. But for bioethanol, they use a yeast. The Candida species has shown a very good glucose capacity of consumption capacity. about 75%, and the ethanol production is in the order of 0.45 grams of ethanol per gram of glucose. It's very similar to the yeast used for the production of beer. And in the final step, the intensification, biocompound recovery and valorization of residual biomass, they used a pretreatment with ultrasound or with ozone. Ultrasound has shown a better performance, but both processes produce a very good efficiency in the process of the biorefinery. The extraction of biocompounds is faster. The energy and solvent residues are reduced, and the quality of the lipids recovered are very high. When they use the pretreatment of ultrasound with two species, Desmodesmus and Tetradesmus, they can produce bioplastics. And these bioplastics have a very good characteristics when talking about elasticity and the mechanical properties. And they have also have the automatization of the production of the biomass in the growth, the pilot scale pond, and they have are able to measure on real time pH, turbidity, dissolved oxygen, and other parameters. They have been working very close to the Newcastle University Working Group, which leads Dr. Sharon Velasquez. And that would be all for my participation. And thank you very much.
Thank you so much.
Thank you very much. I was told that Dr. Gross is around, but I don't.
Yes, I am.
Oh, I'm sorry. I'm sorry. Will you please present your work?
Okay. May I share the screen?
Yes, you can.
Okay. Here we go. Are you able to see that?
Yes, we do.
Yes.
Okay, let me see if I can get it now to grow up
In view.
to be a big slide.
Yes. Okay. It's perfect now.
Thank you very much for the invitation. I prepared a few remarks to describe my activities and my interest to also undertake any kind of collaborative efforts in these areas. So what I like to use my time on is to basically describe what I've done in this area and give you a little bit of background so everybody becomes a little bit familiar with what I do. So my principal interests are in energy and specifically in its economics. And I have focused essentially on very large scale power systems because they have become of tremendous interest, particularly now as the world is trying to decarbonize and trying to get rid of all the emissions. So energy in the form of electricity is one of the most efficient ways to present it. Power systems are really some of the largest systems developed by humans. And in the year 2000, just to give you an idea, the National Academy of Engineering, which is the most prestigious collection of outstanding engineers in the US, named electrification, essentially the development of the vast networks of electricity that powers the world, the most important engineering achievement with the greatest impact on the quality of life during the 20th century. So electricity is very, very critical for that reason. In terms of background, I come from a system theory background. I've worked for a large electric and gas utility company for 20 years, approximately, before coming to University of Illinois, and I've been here since 1993. So with that ado, what I'd like to do is give you some examples of the areas that we have done work, which I think is very, very exciting, in very large-scale computational problems, which have a very strong optimization emphasis. So let me move on to the next slide. And some of the research questions that we focus on is how to realize a modernized, reliable, and efficient grid to deliver the injected generation by the producers to serve the loads which are on the grid. So this is very, very key area, because more than 50% of the transmission system in the United States, for example, is more than 50 years old. So it doesn't have any of the new technology which has been developed, and the modernization of the grid is very, very important, because this is the glue that ties the whole industry together, because for us to get from point A to point B, we have to use the grid. The grid is very big. It's both at the distribution and the transmission level. And I have done quite a lot of work, particularly in the area of reliability, including the linkages between reliability and economics. I've done some work also on the distribution grid. We were consultants, for example, to eBay data center, which was established a few years ago in the Utah system, which is running on fuel cells as their main source of supplies, with the utility being the secondary. And we computed the amazing reliability of that data center, and also the small carbon footprint, just to give you an idea. Given that we have to modernize the grids, the transmission investment decisions become key, and that has been a topic of research for much of the work that I've done. Moving on, in terms of the kind of techniques that we developed for solving some of this problem, has consisted of the development of methodologies for both long and short-term planning, and also for the operation side of the system in terms of getting efficient scheduling and getting effective control of the system. So in that area, I can mention that we did some very important work in terms of hydro scheduling, which, for example, for my old company, saved something like $45 million a year by utilizing the hydro system in such a way to displace as much of the fossil fuel generation as possible, and consequently bring about savings. A lot of resource planning activities where we have to explicitly represent uncertainty. So simulation has become an important tool that we developed in that area, using Monte Carlo type of techniques to be able to represent effectively the uncertainty which is underlying any kind of future planning, because we have to look at a broad set of scenarios to be able to provide robust solutions for what we are doing. Moving on, some of the research questions that we focus on are in terms of computational techniques for large-scale system analysis, simulation, optimization, and control. And those are key questions because, first of all, the large-scale nature means that whatever technique we develop has to scale up. We have to be able to handle the vast amount of data, and particularly when they're used for online applications, those techniques have to do very quick calculations. And so the challenges are great, and we have a number of works both in terms of the scheduling of the system, so in the unit commitment area, but in terms of the dispatch of the system. And now that we have moved into market-based operations, in terms of market operations of the systems that fully take into account the physical characteristics, the large-scale nature of the power system. In the area of market operations, we have done some design of electricity market operations, and also in terms of hedging activities, because markets, you have participants, you don't know exactly what they're thinking today, you don't know what their strategy is. So we have developed some effective auction mechanisms for electricity markets, because we have now probably more than 70% of the load of the United States operating under electricity markets. Mexico, for example, has also gone in the markets area, and many of these countries are adopting the nodal systems in terms of market pricing. From our point of view, we worked on transmission congestion management, because that's becoming a very key problem in terms of how we utilize the transmission. We've also worked on an area which is called ancillary services, which unfortunately is bad English, because this ancillary services are not ancillary in any way. They're absolutely essential services, and without which the transmission system would collapse. But we all copied the British English, and in this case, the British English is wrong, but it's very funny, because I lived in Europe at that time at the beginning of the 21st century, that the European countries have also translated ancillary exactly into the languages. So in all the languages now, we use the wrong term. In terms of hedging tools for electricity markets, we worked in something known as transmission rights, financial transmission rights, in terms of trying to reserve transmission to make sure that we don't have to pay those high congestion charges. So I'd like to talk about the green power system, because that's an important part of how we are going to be decarbonizing the work, where we have done considerable work in terms of the integration of deeper penetrations of renewable energy, which we also combine with demand response, so making the demand be just as much an active participant as a supplier, because if we can curtail electricity, then that electricity doesn't have to be served, and consequently, there's no emissions associated with it. And now lately, we've been working a lot with energy storage resources, the most prominent of which happen to be batteries, because those are being really becoming much more efficient in terms of price. We've seen some amazing reductions of price, much of it due to the fact that there's demand for batteries coming for the electric vehicle adoption and the electrification of the transportation sector. In terms of specific items that we have done in the integration of renewable storage and demand response resources into the grid, we did some interesting studies. For example, how to employ flywheels as a storage resource in the provision of competitive market services, particularly in the area of frequency regulation. And so that was successful, but the big issue with the green power system is that we have to basically manage the flexibility needs of the system, because as we retire many of the fossil-fired units, we need to have controllable resources. And unfortunately, we're not yet at the stage that we can tell the sun to shine when we need it or the wind to blow when we need it. So the provision of flexibility in the system is a key issue, and we've been working on that very, very carefully in the last few years. So in terms of the electric vehicle area, this has been an area of interest for quite some time, because I think very, very clearly the biggest source of pollution that we have now comes from the transportation sector. And it's very, very incumbent on us to try to displace all that fossil fuel emissions that are emanating from the trucking and so forth by electric vehicle. So in this area, we developed a framework to implement the vehicle to grid concept, because we have to integrate these electric vehicles into the grid, not only as a load, but possible supplier of services for the grid. And so that requires the introduction of a aggregator who's going to aggregate collections of electric vehicles to become important market participants. But what has been a big point of frustration so far in terms of the build out of all this electric vehicle load is that the vehicles only recently started selling. And then this year we're running into the problem that people are looking for electric vehicles. And not only are the prices going up with a concomitant rise in prices in terms of gasoline and diesel, but they're harder to find because we have this chip supply problem. But yes, I think you will see a big move towards electric, particularly over the next 8 years, so that by 2030, that's going to be a very important area in which us power system engineers are going to be heavily involved. Beyond the smart grid, because we're all working in the smart grid, we want to build what we call a highly resilient grid to function under very extreme weather conditions. You've heard about the hurricanes year out. Just to give you an idea, in 2021, for example, we had basically the various extreme weather events, including the forest fires in California and in other states that were hit. In Texas, we had the big freeze, and that has very big impact on the network. So the ability to guarantee the delivery of electricity even under the presence of malicious cyber attacks has been of interest. We have worked on some very large research efforts which were funded by the National Science Foundation's Department of Energy and the Department of Homeland Security on the cybersecurity of the grid. It was an effort that spun across 3 other campuses and many departments on this campus. So this is very much of interest, because when we talk about resilience, not only can we maintain the stability of the system, but to be able to restore it to its former state so as not to have either loss of life or loss of economic productivity. So that has become a key interest for us. So I'm not going to take much more time. I have 2 more slides. I'll talk about our work in terms of regulatory policy and legislation, which is very important because we have to bring good technical analytical basis to be able to formulate effective policies. We worked on the big effort that Illinois had to develop the next grid, and we can talk about it when we get together. I'll just end with the slide with this cartoon in terms of after we had the very big blackout on the East Coast in the year 2001. This was one of the cartoons which appeared that everybody started to get very interested in electricity. So I appreciate your attention and thank you again for the invitation. And with that, I'm going to end my show.
Thank you very much indeed. It is now the turn of Dr. Héctor Miguel Aviña Jiménez from the Institute of Engineering of UNAM. The title of his presentation is IDEA Group Sustainable Technological Development. Please go ahead.
Thank you.
Dr. Gross, will you please stop your sharing the screen?
Oh, excuse me. Let me see, where is that? I thought I did. Just a minute. Okay, stop share.
Great, thank you.
Sorry.
Thank you.
Can you see my presentation?
Yes.
Thank you. Well, hello, good morning. My name is Héctor Aviña. I appreciate the opportunity to share the projects that I've been developed in the IDEA group about geothermal direct use. Well, I'm the head leader of the group called IDEA. Our mission is to provide solution in a sustainable way using clean energy through technological development, especially human resource training and knowledge dissemination. We are a multidisciplinary and innovative group of about 40 people, without included researchers or assessors. And our vision is to be a multidisciplinary group that provides integral solution to food, water, and energy sector through applied research. We think that by consolidating Mexican technology, we are looking forward to build the future by renewable ideas. In order to carry out sustainable projects by using the direct use of geothermal energy and other natural resources, we have created this methodology. Our methodology looking for that the social part is well supported, that bring a direct benefit to the people before starting to carry out geoscientific works, talking about geothermal exploration. As a first step, we must focus on knowing the economic activities of the community, what kind of people live in that community, what average age are they, the climate, their tradition and custom, etc. And most importantly, what geothermal energy could solve and how it could help them have a better well-being. The other main point is that the make match between the community's activities economic with the geothermal projects, looking for products or activities that are already managed in the community, which will be those that have the best profitability and can be commercially a quality. This project must have a commercial purpose because we have seen several projects of direct use in Mexico or America Latina of geothermal energy, when use geothermal energy, that if they have government support or some company, this work very well, but if they are no profitability by themselves, they will not be successful. Once the project is identified, a market study is recurring together with analysis of the opportunity against the competition, where the product can be sold, and then what kind of added value we will have to make to product with geothermal energy. And the next step will be to carry out the business plan, considering inputs and outputs of money, investment, useful life, among others. Now, I will explain how we have following this methodology into the practice. The project that we have more advances is the geothermal food dehydrator. This is a history resume of the installation of geothermal food dehydrator. Everything started around 2012, where we did the laboratory test. They were more academic research studies with which we are able to obtain a prototype that can be installed in the field. In 2017, we were able to install the first DGA, or the geothermal food dehydrator 10. We call it DGA 10. With which we will obtain up to 10 kilograms of dehydrated products per day. With this project, we can give 5 jobs, were direct generation in 2018 and 2019. We can make a semi-industrial dehydrator, DGA 200, with which 50 jobs were generated directly, and with which we were able to obtain up to 200 kilograms of dehydrated products per day. And by 2020, thanks of the good results we have from to the semi-industrial dehydrator, we were awarded the Prodetes Award from the World Bank, which we won together with one of the spin-off companies from the Engineering Institute called Ingenera. With this award, we are able to install the DGA 600, which is a level dehydrator industrial that can dehydrate up to 600 kilograms of products per day, and is directly generating 60 jobs. These are some pictures from the tested of DGA 200. We really like to show of this picture because they show us that the dehydrator works during the day, at night, if there is wind, if there is no wind, if it's cloudy. It is the advantage of use the geothermal energy. They work 365 days per day and 24 hours per day. And in this project, 90% of the jobs that are generated for women. With this project, we help to empowerment of women, and they can select the job that best suit them. These are some pictures from the test of DGA, excuse me. This is the picture of DGA 600, which was inaugurated 2 years ago. The geothermal food dehydrator company of Nayarit had to be created so that they could operate and could hire the people who were working in this plant, was built and made Mexican technology. Also, everything is manufactured by Mexican. Deshidratador Geotérmico de Alimentos is the company in charge for the commercial operation of the food dehydrator plant, managing and offering the products of the international markets. And for local markets, the brand Geothermal is the only which manages distribution and promotes the final dehydrated products.
2 minutes left.
We have several projects in progress. There are the ones with the greatest development. The first is the modular geothermal desalination plant, which, like the dehydrator, we will take it to the semi-industrial level, and then in short term take it to an industrial level. For the moment, we already have the engineering and everything necessary for install modular geothermal desalination 40. We can obtain 40 meters cubics per day of fresh water, and this year we will install it in Los Cabos, Baja California. The second project is the binary cycle IDEA 10 kilowatts. We'll call it IDEA 10, up to we working in the IDEA 100 to can produce 100 kilowatts, and which we hope to install this year. With this kind of project, we will have the possibility of putting projects for direct use in insulation and outside the electricity grid. And the heat pump mix, it's the name. This is the name of the project. The following project is focused in heavy equipment manufacturing in Mexico for the air condition of a space for energy saving using the thermal energy of subsoil. And the moment we have manufactured geothermal heat pump of 3 tons of refrigeration, and we were manufacturing of 10 tons. These 3 projects are being financed by the Mexican government through CONACYT. And finally, we are working on the manufacturing of craft beer. The use of geothermal energy for the production of craft beer, we allow the use of geothermal heat in different stages of the production, depending on the energy levels found in the different geothermal points. The goal is to reduce energy costs, and in addition, the option of exchanging non-national agricultural raw materials used in the process for products that originate and are producing with the country, especially in areas close to geothermal resources, in so encouraging the agricultural part and the regional economy. Well, thank you very much for your attention.
Thank you very much. It is now my pleasure to introduce Dr. Rosa Maria Ramirez Zamora from the Institute of Engineering. She's by director, by the way, of the UNAM. The title of her presentation is Air and Water Treatment without a Simultaneous Production of Hydrogen by Chemical and Photochemical Processes.
Thank you very much, Dr. Victor Castaño. Can I share my screen, please? Okay. Okay. Well, good morning, everyone. My name is Rosa Maria Ramirez Zamora. I work in the Environmental Engineering Department of the Engineering Institute of Universidad Nacional Autónoma de México, UNAM. I am very happy to participate in this symposium on energy organized by Dr. Chamorro and Dr. Castaño on behalf of Illinois University and UNAM, respectively. I thank both for inviting the academic staff of the Engineering Institute to participate in this symposium. And I also thank the authority of both universities for making this possible. I hope it will be very successful to reach the objectives that have been set up. The title of my work has been already mentioned by Dr. Castaño, so I move on. What, just a minute? Okay. Before describing my research projects on energy, supported mainly by my university and performed through the academic collaboration with several entities of my university and also other universities. I would like to mention the facts that we take into account to start investigating in this topic. So first, Mexico is one of the most promising countries in the field of solar photovoltaics due to its high solar radiation, around 5.2 kilowatts per hour per square meter. Also, Mexico is the world's largest producer of silver in the world and a top global producer of gold, copper, zinc, among others metals. So as a result of this production, Mexico is also one of the largest producers of residues and metallurgical byproducts. Oh, sorry. So the residues and metallurgical byproducts have transition metals as iron, copper, titanium. These materials can exhibit catalytic and photocatalytic properties. So they can use it as raw material to prepare microcomposites using the green chemistry principles, and also they can use it as catalyst and photocatalyst for water treatment with a simultaneous hydrogen production, and this means an eco-friendly process. In our group, we have used these materials without making any modification to treat water, and also with low organic pollutant contents under oxidant conditions using UV radiation and also different kinds of oxidants. And also we had treated wastewater with high organic pollutants contents under reducing conditions using UV radiation and also solar lights, and also nitrogen to obtain our reducing conditions. Also, we had treated air polluted with organics, and under thermochemical processes, we had obtained also hydrogen. This slide illustrates the experimental setups that we had used in collaboration with the National Institute of Technology to produce the degradation of low organic pollutants contents. This is a raceway reactor, which is located inside of a solar simulator light, and the controlling of the radiation is possible through this system also. Also on the right side, we have a picture of our system for the degradation of organic pollutants at high concentration in wastewater or water using reducing condition. This system has 3 white light lamps and 3 UV light lamps, and photoreactor, a power source, and also the outlet of this reactor is connected to a gas chromatograph for the monitoring of hydrogen and other types of gases. On the other hand, this slide illustrates another experimental setup that we had used in collaboration with the National Institute of Nuclear Science, which is equipped with 5 different types of gas for making the dilution of air polluted with alcohols, among other pollutants. This system also has an oven to evaporate the pollutants, which is sent to the reactor, and we have a control system of the temperature, and this system is also connected to a gas chromatograph for monitoring the production of hydrogen and other gases produces in the system. About our academic collaboration in hydrogen production, we had partners both in Mexico and in Spain. One of the papers that we had produced with our partners shows the potential of our network in the photocatalytic production of hydrogen, using in this case a solar pilot plant and a photocatalyst of gold, supported on Titania, which was developed by the Institute of Applied Science and Technology in Mexico and used it in the solar platform in Almeria, Spain. That work searched to measure the efficiency of the gold photocatalyst for the simultaneous hydrogen production and organic pollutant removal from aqueous solution under direct solar irradiation at a pilot scale plant. The pilot plant was composed of 15 Pyrex glass tubes mounted on a fixed platform at 38 degrees, which is the local latitude in the solar platform in Almeria, Spain. During the experiment, formic acid, glycerol, methanol, and also a municipal wastewater and industrial wastewater were used as sacrificial agents in the reaction. The results show that the highest production of hydrogen was achieved using a 0.05 molar formic acid solution. The best hydrogen production gave an energy efficiency of 1.8% chemical energy accumulated in the form of hydrogen versus the solar energy arriving to the photochemical reactor. Then we continue collaborating with the Institute of Applied Science and Technology, ICAT, and to join forces with the Centro de Investigación Estudios Avanzados, INVESTAP. In fact, as a result of this collaboration, we direct together one doctoral thesis and a publication called Photocatalytic Hydrogen Production in a Solar Pilot Plant. I'm sorry, I didn't move up. And characterization and evaluation of copper slag by functional photocatalyst or alcohol degradation and hydrogen production. The paper deals, yes, with the valorization of 2 byproducts, one from the metallurgical industry, the copper slag, and the other from the mezcal industry, the residual alcohol. Thus, the first residue was used as catalyst in the photocatalytic split of water to produce hydrogen, using the second residue as a sacrificial agent. The work consisted of extensive characterization of the material, and which in general were acceptable as photocatalysts, with the exception of the specific surface because it was very low. The experiment using UV and simulated solar light showed that efficiency of the residue is higher in the visible range, and the hydrogen production increased in the order. Methanol is higher, then continues with propanol and others alcohol, which corresponds to increase of the hydrocarbon chains or alcohols. An apparent quantum yield for methanol degradation of 40% under simulated solar light was obtained, which is similar to data reported for some expensive nanocatalysts prepared in laboratory. This provides the prospect for a low-cost and potentially efficient photocatalyst for the oxidation of organic pollutants in industrial wastewater under solar radiation with the simultaneous hydrogen production. And finally, as already mentioned, we also collaborate with the Instituto Nacional de Investigaciones Nucleares from this alliance with graduate and master students, and the results were published in a paper, which is colored one-dimensional platinum's oxide cerium nanorods catalyst for hydrogen production by steam reforming of methanol, the effect of the platinum precursor. To do that, the platinum nanocatalyst was supported on oxide cerium, was synthesized and evaluated in the steam reforming of methanol reaction that produced hydrogen. And the effect of the precursor was investigated using 3 different salts. The best was produced with the hexachloroplatinic acid, even though the allowed catalytic activity was observed in this case for the methanol degradation. That this was due to the formation of oxychlorinated species. But a stable methanol conversion was observed during the reaction. No further changes in the outlet signals of a real-time monitoring analysis by mass spectrophotometer was observed. Thus, this indicates that the catalyst was very stable during the reaction. And so that's all. I would like to thank you for your attention, and thank you very much again.
Thank you very much. Next presentation is entitled Buildings Energy Efficiency, and is presented by Dr. Guadalupe Wells Lesbros of the Institute of Renewable Energies of the National University of Mexico. Dr. Wells.
Okay, thank you. It says that I can't share my screen. Can you give me permission, please? Okay, thank you very much.
Doctor, are you available to share your presentation?
It seems to.
Yes.
Let me, yes? Okay, yes. Thank you very much. Good morning. Thank you very much for the opportunity to share the work and the vision of the Building Energy Group of the year UNAM. I am Guadalupe Wells, and I said to you that in our group, we carry out basic research with the aim of understanding and describing the heat transfer and ventilation in buildings. We realize applied research to improve the thermal comfort conditions inside building and to reduce the use of energy for heating, cooling, and lighting. We have created tools and methodologies for evaluating the thermal performance of building envelope components as inner habitat that you can access by internet. Our methodological basis for energy efficiency in buildings is the bioclimatic design. This is the design of the building according to the climate of the place where it will be built. This includes the geometry, orientation, use of solar control, window size and location, color of the outdoor surface of the envelope, etc. We favor the use of passive and low energy consumption systems over HVAC systems. We have contributed to the designs of buildings using this philosophy. In collaboration with the University of Sonora, and the Lawrence Berkeley National Laboratory, we have designed, and now it is being built in our institute, a demonstrative bioclimatic building for hot subhumided climate. We are developing low energy cooling systems to be placed in that building. For example, automatic night ventilation, evaporative cooling plus occupation ventilation, air tubes, radiative cooling. Here we have renders of the buildings, renders of the evaporative cooling plus occupation ventilation, and this is a photograph of the building as it is by now. We also are developing the data acquisition systems for building monitoring in order to evaluate air quality and hydrothermal, luminous and acoustic environmental conditions, and to measure energy and water consumptions in this demonstrative building. Our group is integrated by 4 researchers, but we have the collaboration of many students and professionals and postdoctoral. So thank you very much for your attention.
Thank you very much, Doctor. And the next presentation is by Dr. Ivona Yashuk from the University of Illinois. The title of the presentation is Materials and Structures for Energy and Sustainability.
Yes, thank you very much for the invitation. I'm trying to share my screen.
We can see your screen.
Okay, great. All right. Well, hello, everyone. It's great to speak to you. I really enjoyed the presentation so far. And I am excited to tell you about my research on materials and structures for energy and sustainability. So I'm professor in the Department of Mechanical Science and Engineering at the University of Illinois. My research addresses materials. So I look at different types of materials and both engineering and biological materials. And I do both modeling and characterization. In particular, I'm interested in studying materials at different structural scales to understand their processing, structure, composition, property relations. So here is a list of techniques, some representative methods, characterization methods, and applications are in various areas, and I will focus today on energy. Regarding the materials, we look at synthetic materials for these various applications. High temperature polymers, conducting polymers, polymer composites, bio-inspired materials, architecture materials for lightweight and highly conductive materials, and so on. A big component of my research is additive manufacturing, utilizing the flexibility of additive manufacturing process to create new structures and new materials. And some of my work also is in biomechanics, medical applications. I noticed that this group will also be, this program will also include biological aspects, so I look forward to learning more on that. So here is first example of my work on energy, materials for energy. This is research is specifically on novel high voltage, high temperature materials and structures. And this has been part of an industry university cooperative research center sponsored by National Science Foundation. The idea of those centers, there are about 80 of them in the US, and the idea is to bring together industry and academia to solve important problems. So that the goal, the objective, the vision of the center was to develop, to analyze, to invent novel materials for energy transfer and other applications. So regarding energy transfer, the focus was mainly on power transmission, both underground and above ground. And so it included mainly focusing on the structure of the cables, as well as monitoring of the whole structures and protection of such structures, especially against impacts. So the idea here was to come up with more conductive alloys, with robust polymers that would withstand environmental effects. These structures should last 50 years, and actually a lot of US infrastructure is aging, needs replacement, so that was one of the motivations. And the idea, of course, was to protect against the environment, high winds, freezing, and ice and others. And then we also combined it with aerospace industry, because aerospace industry can also benefit from high voltage, high temperature materials. There's a lot of weight in a plane is due to cables. Those cables could be lighter, then the planes would be lighter, and there would be savings of energy. And also, so it's the savings of energy, and also, lightweight in general. So materials that would be comparable to existing materials and at light. I'm trying to move my slide. Yes, and another big area that is of high interest to me are biological materials, and for the purpose of studying, understanding better nature, but also for design of bio-inspired materials for various applications, including energy and sustainability. And biological materials have very interesting characteristics and structures. They are much more rich from a fundamental viewpoint than traditional materials. They are more multifunctional, hierarchical structures, composite, the interfaces, porosities, functionally graded characteristics, fluid-filled characteristics. They are adaptive, self-healing. So we are learning about these materials, how to use these ideas from nature for these various engineering applications. And also, some of the materials from nature can be used directly or indirectly in various engineering applications. And here's just a schematic of various features that are quite common for lots of biological materials. So understanding these features, one can implement them in designs of new engineering materials. So what's one such example is design of new materials for turbine blades. And this is a collaborative work with Chamorro. And so the idea here is to use the sandwich structure idea, and also even biological materials such as wood with combination with this novel high temperature polymer, and come up with material structures that will be comparable to and exceeding the existing designs, and allow for to withstand adverse environmental factors. So the idea again is, as mentioned, I'm interested in multi-scale aspects, so starting from lowest scale, which would be as fiber level, and then going to the ply level and the design of various plies, and finally a design of the whole blade. And this is a combination of experiments and theory. With additive manufacturing, we can create various structures with various architectures. So we've been exploring these triple periodic minimal surfaces, but also look at many other designs. And these designs are found in nature. And we 3D print them, we test them, we model them, and look at the various multi-field properties. And regarding applications, porous materials, these are structured porous materials, can be used as insulation, energy storage, filtration design, devices, heat exchangers, lightweight structures, among others. And here is just a brief mention of these novel polymers. So we've been exploring them for these various applications, and they have pretty impressive characteristics: very high temperature, low water absorptions, and many other features. And an important feature too is that it has properties comparable to thermal sets and not exceeding, and yet can be remelted and recycled. And also it can self-heal and bond. And we are also exploring nano effects in materials and how architectures of nanofillers can tailor properties. And such fillers can be synthetic fillers, or they can come from nature, such as cellulose and other materials. So that concludes my presentation, and I'd be glad to answer questions now or later. And my contact information is enclosed.
Thank you very much. I take this opportunity to ask again to put your questions in the chat. We will be distributing all the full data of every single speaker today. And also would like you to take note of potential collaborators, because the whole idea of this event is to establish these joint proposals between UNAM and UC scholars. Thank you very much, Doctor. Next speaker will be Dr. Iván Moreno Andrade from the Instituto de Ingeniería of UNAM, and he will be talking about biohydrogen from organic solid waste.
Dr. Castaño, Dr. Iván is in room 1 and he can move to this room. Can you help?
Yes, of course.
Thank you.
Okay, let's wait a minute or two for him to move to this place. We are just on time, so there is no problem. And let's wait for 1 or 2 minutes, and if not, we ask Dr. Valdez Vasquez to present, and then Dr. Moreno will be the last of the session. Let's wait a couple minutes.
Dr. Ivan?
Ivan Moreno?
Yes.
Are you here? Are you here? I don't see him.
Dr. Ivan tell me that if he's in room one, he can move it.
Okay, I will check.
Okay, if you agree, and if she's willing to, I will then ask Dr. Idania Valdez Vasquez to present, so to switch her slot with Dr. Moreno. Are you willing to do that, Dr. Valdez?
Yes, I'm fine.
Thank you very much. The title of her presentation is, she's also from the Institute of Engineering of UNAM, and
yes.
The title is butanol production from lignocellulosic biomass and C1 carbon sources. Please go on.
Can you see my presentation now?
Yes, we do. Thank you.
Thank you. Thank you. Good afternoon to everyone. Thank you for the invitation to this symposium and the opportunity to talk about my research projects about butanol production from CO2. My research is focused on green drop-in biofuels like butanol. Before becoming an attractive biofuel, butanol should be produced from a widely renewable and cost-effective source, such as biomass. The typical route for butanol production from lignocellulosic biomass includes a pretreatment, enzymatic hydrolysis before fermentation. Depending on the pretreatment, a detoxification stage could be necessary. However, the pretreatment hydrolysis enzymatic increase the production cost and the capital investment. As an alternative, I propose an advanced biorefinery in which 3 microbial consortia consume different fractions of the polysaccharide, producing hydrogen, methane, and butanol. Before talking about this particular biorefinery, I want to share with you some results about the availability of agricultural biomass in Mexico. Past years, I had the opportunity of traveling to the largest agricultural areas in the country. In total, I visited 11 sites to record how much biomass is generated, which inputs are used, such as water, fertilizer, among others, and the currently uses for sugarcane bagasse, corn stubble, wheat straw, and agave bagasse from the tequila production. With this information, we estimated the available biomass for biofuel production. Also, I used logistic tools to determine the possible localization and capacities for these biorefineries. In total, I estimated that it's possible to start 34 biorefineries located over all the country. For more information, you can see this publication. Now, how I mentioned previously, my research is focused on consolidated bioprocesses for production of butanol. Unlike other configurations, I do not use typical pretreatments. Instead, after milling, a microbial consortium integrated by indigenous bacteria hydrolyze and ferment the hemicellulosic fraction, producing hydrogen, CO2, and organic fatty acids such as acetate and butyrate. Now all the substrate is consumed. Therefore, a second microbial consortium hydrolyze and ferment cellulose, producing butanol. The problem is the typical hydrolytic bacteria do not produce high amounts of butanol, and fermentative bacteria do not hydrolyze cellulose. To solve this problem, some researchers have used different approaches to produce butanol directly from cellulose. My research group has used microbial consortium. On the first try, we used an acidogenic consortium, and by controlling the pH, we produce butanol with a similar concentration than genetically modified bacteria. Then we use bioaugmentation with Clostridium, Saccharobutylicum, and Clostridium-based Jirinki. And the butanol concentration was very similar, even higher, than using co-cultures. However, our best result was found through the use of butanol-tolerant microbial consortium, producing 14 grams per liter, which is the highest amount reported so far. This butanol-tolerant microbial consortium is integrated by hydrolytic and fermentative bacteria. And more importantly, Pseudomonas is present in this microbial consortium. Past studies indicate that Pseudomonas produce EPS, extracellular polymeric substances, which help bacteria tolerate the butanol presence. Going back to the biorefinery scheme, despite having promising results in the butanol production, the overall yield is very low. Only 10% of the substrate is converting into butanol. One reason is because most of the carbon is lost in form of CO2. This in this part. As a consequence, I became interested in the Wood-Jundal pathway, or the cetogens. In this pathway, CO2 is used as the carbon source. The resulting products are different kinds of alcohols, one of them butanol. In 2020, we published a study about the effects of 3 inocula on butanol production from CO2. In the first stage of experimentations, we used a culture medium containing urea, which was useless for butanol production. Then, after day 140, we changed the culture medium to another one containing trace metals. That's when we finally could find some butanol. Sadly, the concentration was very low. However, I'm interested in keeping on studying this process in continuous reactors to increase the butanol production. Finally, I would like to talk about the ongoing research in which we are studying how these kind of biorefineries could be economically feasible and sustainable. In the first model, butanol, electricity, and steam are produced, and CO2 is emitted to the atmosphere. In the second, the gas fermentation bioreactor uses the CO2 to convert it into more butanol. And in the third, the gas fermentation bioreactor uses the CO2 to produce caproate. Caproate is a medium chain fatty acid, more valuable than butanol. This table summarizes the main economic results. And the first, I want to highlight that it's possible to duplicate the butanol production by using the CO2. However, also it's necessary to duplicate the capital investment and the operating cost. The investment is 3 times higher if we select the caproate production and 2 times higher the operating cost. By process simulation, we also are able to determine the environmental indicators such as water consumption, wastewater quality, greenhouse gas emissions, energy efficiency ratio, among others. And with all these indicators, we are identifying pros and cons of the 3 biorefinery models. With this, end my participations. Thanks a lot for your attention.
Thank you very much. And then I guess Dr. Ivan Moreno Andrade is already at this room?
Yes, that's right.
Okay, thank you very much. You will have the honor to present the very last talk. And after you finish, I would like to say a few words, if you allow me. Please go ahead, I already presented you.
Okay, thank you very much. And apologize because I had a problem with the computer. I changed the computer, but I just re-enter into the group 1 and I just wait for the access to this meeting number 2. And I feel that everybody can see my presentation. Then today I will be the last one that I will talk about some topics that has been mentioned by other colleagues, but I will focus in this presentation about the biohydrogen from organic solid waste. I'm working at the UNAM, at the Institute of Engineering, in the state of Querétaro, in Juriquilla campus. Well, in my group, we have been working in the anaerobic digestion for organic solid waste, focusing in different areas, mainly for the organic waste treatment, but also, as other colleagues, in the gaseous biofuel production, mainly hydrogen and methane. But also, we are very interested in to use the final subproduct that we have in this process to use it as a biofertilizer. Then we are not only working in the biogas production, but also in the microbiology, the optimization of the process, and to obtain this the treatment of the waste. Well, as other colleagues, as Simon Gonzalez talked a couple of hours ago, we produce a lot of organic solid waste, and in this case, the organic solid waste represent around the 50% of all the waste, the municipal waste that we are producing in our countries. In this sense, we try to use this waste for the biohydrogen production, but not only the biohydrogen is produced in this kind of reactors. We also have some liquid and the effluent of these reactors has some soluble organic matter and products that can be value added as volatile fatty acids, that lactate and other solvents that other colleagues talked to you in the previous talks. As Dr. Aidania's presentation referred, the biohydrogen is part of the biorefinery concept. The idea is we can produce a lot of subproducts using the biorefinery, but in our case, we are focusing in this biological conversion to obtain different subproducts. And in this sense, we with the dark fermentation, we can apply a lot of the different substrates, as we saw during the symposium, other example as an algae, but we are focusing in the organic solid waste, and I will talk about the food waste, and to use for the biohydrogen production. But we can obtain a lot of value-added products. In this sense, we have been working with the organic fraction of the municipal solid waste, but it is interesting because the solid waste has, depending on the origin, will have different characteristics. It's not the same, the waste that is coming from municipal landfills, for example, and to the food market. In this sense, we have been working with the organic fraction of municipal solid waste coming from the recycling factory here in Querétaro, that is producing more than 300 tons of this kind of waste. And this we are working with this waste that is not only organic solid waste, but also have some quantity of paper, plastic, and glass in this kind that could be a very, very different that other kind of substrates. But the idea is to obtain the biohydrogen and other products. We also have been working with the central regional market here in Querétaro. And as of course, you can see there are a lot of vegetables here, and also food waste coming from different restaurants and cafeterias here in Querétaro and from the university. And also we have difference with the composition, and this result in differences in the biofuels production. In this sense, we are working with different systems, including batch, continuous, and discontinuous processes, and we are working to develop some different type of pilots to obtain the maximization of the biofuels production. And in the case of biohydrogen production, we are working on the operational parameters optimization, different strategies as the augmentation of the microorganisms, the co-digestion, and other control strategies. And I will talk just a couple of minutes for the optimization. And I feel Brenda is turned on the microphone. And in this sense,
can you mute yourself?
And then we have been working to obtain the parameters into the process to optimize the biohydrogen production, obtaining the best performance of the reactors. But also, we have been working on control strategies to obtain and control the bioprocess to maximize the biohydrogen production. We have been working with in collaboration with the Professor Alejandro Vargas, that is expert in control of bioprocess, the bioprocess control, and we are developing some control strategies to maximize the biohydrogen production. In this idea, we not only have been working in biohydrogen, but also in the methane production. And the idea is to obtain the two biofuels into a stage process and to try to have the stable and efficient operation of this kind of reactors. And also, as I had told you at the beginning of the presentation, we also are looking at to use the digestate, that is the last subproduct of this process, as a biofertilizer, and we have been using this for how to apply into the soil, not only as a biofertilizer, but also as a soil conditioner to improve the soil's physical qualities. And we have different projects also in this kind of process, and we are trying to we are working on an innovation program to transfer some of this technology that for the control into maximize the quality of the biofertilizers. Then, as a conclusion, well, the main conclusion is that we are interested in biohydrogen production and value-added products, including not only biohydrogen, but methane, volatile fatty acids, and other solvents, but also the biofertilizers that we can work at the end. And of course, to use the biohydrogen, the fermentation to produce biohydrogen as a initial platform into a biorefinery. Just to thanks to the students and the colleagues that are working on this kind of this project with me, and thank you for your attention. I will be open for questions or something like this. Thank you, Professor Castaño.
Thank you very much. We have been asked to move back, all of us, to room 1. Please do so for the closing ceremony, and then we meet there again. So please look at your control and move back to room 1, please. I'll see you there in a few seconds.